You are 40 light-years from Earth, and the world ahead of you shines with a blue so deep it looks like a sapphire suspended against the darkness of space. From this distance, the planet appears peaceful, beautiful even, with its cobalt atmosphere wrapped around a sphere slightly larger than Jupiter. You drift closer in your observation vessel, and instruments begin registering wind speeds that seem impossible, numbers climbing past 8,000 kilometers per hour. This is HD 189733b, and the blue color that makes it look so inviting comes from something that would destroy anything exposed on the surface in moments. The atmosphere here is not made of familiar gases arranged in familiar ways. Silicate particles form at high altitudes where temperatures exceed 1,000 degrees Celsius, and these particles are what create the deep blue haze you see from orbit. The silicates are essentially glass, forming in clouds and falling through the atmosphere, but the winds are so fierce that rain never falls straight down. Instead, glass particles slash sideways through the air at speeds that would exceed the fastest winds ever recorded on Earth by a factor of 7. So yes, on this planet, glass really does rain sideways at speeds approaching 9,000 kilometers per hour. You are listening to the Drowsy Astronaut, and tonight you are going on a slow journey through the strangest worlds astronomers have discovered, real planets orbiting real stars. Places where nature creates conditions that challenge everything we thought planets could be. We will move slowly through 200 facts about worlds with molten surfaces, freezing skies, rubies falling from the clouds, iron and glass rain, and planets that drift through space without a star of their own. If you're still awake later, feel free to share in the comments where you are listening from. And if you enjoy these journeys, a like or subscription help others find their way here too. But for now, you are drifting in space near a planet where glass rains sideways. And there are many more strange worlds waiting ahead. The blue world fills your viewport now, and you can see bands and swirls in the atmosphere, patterns created by the relentless winds. The planet is tidally locked to its star, which means one side always faces the stellar surface, while the other remains in permanent darkness. On the day side, the star hangs motionless in the sky, blasting the surface with radiation and heat. The night side never sees the star at all, and temperatures there drop hundreds of degrees lower than the scorched hemisphere facing the light. Between these two extremes, the atmosphere tries to balance itself. Hot air from the day side rushes toward the cooler night side at tremendous speed, and cooler air cycles back in a pattern of circulation that never stops. The glass particles caught in these winds become weapons, moving fast enough to strip away any surface they encounter. Astronomers measured these wind speeds by observing how light from the star changes as it passes through the planet's atmosphere during transits. And the data revealed motion faster than anything in our solar system. You move away from HD 189733b and set a course for a planet that makes even that glass rain world seem mild. KELT 9b lies over 600 light-years from Earth, and as you approach its star system, the heat becomes the dominant fact of existence here. The planet orbits a star much larger and hotter than our Sun, and it circles so close that temperatures on the day side reach 4,300 degrees Celsius. That temperature is hotter than the surface of many small stars, and it creates conditions that break apart the very molecules that form the atmosphere. The planet stretches out before you, a massive world nearly 3 times the radius of Jupiter. On the day side, molecules like hydrogen and water vapor do not survive intact. The heat rips them apart into individual atoms, and only on the cooler night side can these atoms recombine into molecular form. The planet is slowly evaporating, losing material into space at a rate that astronomers can measure, and over time, this world will lose a significant portion of its mass to the stellar wind. You are looking at a planet that is literally being disassembled by heat. Observations from multiple telescopes have detected vaporized metals in the upper atmosphere, including iron and magnesium. Materials that on Earth exist as solids, but here float as gases, high above the surface. The entire day side glows with thermal radiation, and if you could somehow stand on the surface, the ground beneath your feet would be hot enough to melt most known materials. No solid surface could remain stable under these conditions, and what lies below the atmosphere is likely a roiling ocean of molten rock and metal. The star itself looms enormous in the sky from the planet's surface, appearing much larger than the Sun does from Earth because the orbital distance is so small. KELT 9b completes one orbit every 36 hours, racing around its star at speeds that keep it constantly bathed in intense radiation. The planet's atmosphere is being stripped away by this bombardment, and in the distant future, if the planet survives long enough, it may be reduced to a bare core with no atmosphere left at all. You leave the evaporating giant and travel to another system where a planet is being consumed in a different way. WASP 12b orbits its star so closely that tidal forces have stretched the planet into an egg shape, and material from the atmosphere is being pulled away toward the star in a steady stream. The planet is not spherical anymore, and from a distance it looks distorted, elongated in the direction of the star that is slowly devouring it. The planet loses approximately 6 billion tons of mass every second. That number is difficult to grasp until you realize that at this rate, the planet will be entirely consumed in roughly 10 million years. For a planet, that is a short remaining lifespan, and astronomers observing this system are watching a death in progress. The material pulled from the planet forms a disk around the star, and some of it eventually falls onto the stellar surface, feeding the star with the substance of its own planet. You drift closer and notice the dark color of the planet's day side. The atmosphere here contains more carbon than oxygen, which is the reverse of what Earth's atmosphere holds. And this carbon-rich composition creates conditions that may produce exotic compounds. Some researchers think the atmosphere could contain particles of soot or even tar, materials that absorb light and give the planet its dark appearance. The temperature on the day side exceeds 2,500 degrees Celsius, hot enough to vaporize most metals and keep the surface in a state of permanent molten chaos. The star dominates the sky here even more than at KELT 9b, filling a huge portion of the visible hemisphere and pulling at the planet with gravitational force strong enough to reshape its entire structure. Tidal heating from this constant gravitational stress adds even more energy to the planet, keeping the interior hot and possibly contributing to the mass loss. The planet's orbit is gradually decaying, which means it is spiraling slowly inward, and the rate of material loss will likely increase as it gets even closer to the star. You turn your vessel toward a planet discovered orbiting the remnant core of a dead star. Kepler 70b survived an event that should have destroyed it completely. The star it orbits was once a red giant that expanded outward during the final stages of its life, and the planet was likely engulfed within the outer layers of that expanded star. Somehow it survived, and now it orbits a white dwarf core at a distance so close that surface temperatures reach 7,000 degrees Celsius. The planet is small compared to the gas giants you have just visited, and it orbits its white dwarf star in only 5.76 hours. That orbital period is one of the shortest known, and it means the planet experiences a year that lasts less than 6 hours. The surface is almost certainly molten, with no solid ground anywhere, just heat and radiation and the faint light of a dying star. The white dwarf itself is dim compared to a normal star, but the planet orbits so close that the heat remains extreme. From the surface, if you could somehow stand there, the white dwarf would appear enormous, filling much of the sky with its pale light. The planet is thought to be the leftover core of a gas giant, stripped of its outer layers during the red giant phase, and left as a dense remnant orbiting in the habitable zone of stellar death. Observations of this system have revealed a second planet, Kepler 70c, also orbiting close to the white dwarf, and together they represent a planetary system that survived total destruction. You move onward to 55 Cancriae, a world that orbits its star in only 18 hours and may have a surface partially covered in flowing lava. The planet is roughly twice the diameter of Earth, but 8 times more massive, and it circles so close to its sun-like star that the day side reaches temperatures around 2,000 degrees Celsius. Observations have detected significant temperature variation between the day and night sides, with swings of more than 1,000 degrees, and the atmosphere may transport heat in ways that create extreme weather. The planet's composition is thought to be rich in carbon, which has led some researchers to suggest the interior might contain layers of diamond and graphite under intense pressure. This remains uncertain, but the carbon-rich chemistry would make the planet very different from Earth's silicate-based composition. The surface may feature lakes or seas of molten lava, and the high temperatures would keep rock in a liquid state across large regions. The star hangs huge and brilliant in the sky, never moving from its fixed position, and the planet rotates in sync with its orbit, so one face is always turned toward the light. You set course for COROT 7b, the first rocky exoplanet ever discovered, a world that opened astronomers' eyes to the variety of solid worlds beyond our solar system. The planet is about 60% larger than Earth, and it orbits a star similar to the Sun, but at a distance 50 times closer than Earth. The dayside temperature reaches 2,500 degrees Celsius, hot enough to vaporize rock, and the night side is far cooler, though still inhospitable by any Earth standard. On the day side, the surface may be covered in lava that glows red and orange in the starlight. Some models suggest that rocks on the day side evaporate into the atmosphere, and as this vapor is transported by winds toward the cooler night side, it condenses and falls as a rain of pebbles and stones. The idea of a place where rocks rain from the sky seems impossible, but the temperatures and pressures here make it plausible. Sodium and potassium have been detected in observations of the planet, elements that would exist as vapor in the extreme heat. You are looking at a world where the familiar substance of stone behaves like water on Earth, evaporating in heat and condensing in relative coolness. The planet's surface is constantly reshaped by these processes, and there is no stable ground in the way Earth has stable continents. Everything flows, everything changes state, and the boundary between solid and liquid and gas shifts depending on location and temperature. The star burns steady and close, and the planet endures conditions that seem designed to prevent any kind of stability. Your final destination in this part of the journey is WASP-18b, a massive planet that is spiraling inward toward its star and will eventually fall into the stellar surface. The planet is more than 10 times the mass of Jupiter, and it orbits so close to its star that tidal forces are pulling it inward at a measurable rate. Astronomers calculate that the planet has less than 1 million years remaining before it is consumed, which, in cosmic terms, is an eye blink. The planet's immense mass creates a gravitational tug on the star itself, causing the star to bulge slightly in the direction of the planet. This interaction generates heat through tidal friction, and both the star and planet are affected by the exchange of energy. The planet's atmosphere is likely being stripped away by the intense stellar radiation, and the surface temperature is extreme, though not quite as high as some of the other worlds you have visited. The orbital period is less than 1 Earth day, and the planet races around its star in a doomed spiral. You can see the star from the planet's surface as an overwhelming presence, a wall of light and heat that covers a huge portion of the sky. The planet is locked in its orbit, always showing the same face to the star, and the day side is blasted continuously with radiation. The night side experiences a brief respite, but the heat from the day side circulates through the atmosphere and keeps even the dark hemisphere far too hot for any familiar form of matter to remain stable. This is a world in its final stage, and observing it offers a glimpse of planetary death by stellar consumption. The heat, the proximity, the tidal forces, the evaporation, the orbital decay, all of these worlds share the common thread of existing at the extreme edge of what a planet can endure. They orbit too close, burn too hot, lose too much mass, and yet they exist. Real objects circling real stars, some of them discovered only in the last decade or two. Telescopes detected them through transits, radial velocity measurements, and direct observation, and each discovery added another example of strangeness to the catalogue of known worlds. The universe creates planets in configurations that early models did not predict, and these scorched giants and evaporating cores represent conditions that stretch the definition of what a planet can be. As your vessel moves away from the heat and toward regions where other kinds of strangeness await, the stars around you remain steady and distant, And the journey continues without pause into the next realm of cosmic oddity. You are now entering regions of space where planets have atmospheres that behave in ways no Earth-based weather could replicate. The world ahead appears as a dark shape against its star, and as your instruments begin scanning the atmospheric composition, data streams in showing iron vapor at high concentrations. This is WASP 76b, a planet where metal falls from the sky, and you are approaching the boundary between its permanent day and night sides. The terminator zone stretches below you like a line dividing two completely different environments. And it is here that the strangest weather occurs. On the day side, temperatures climb to 2,400 degrees Celsius. At this temperature, iron does not exist as solid metal, or even as liquid. It becomes a vapor that mixes with the atmosphere and rises into the high-altitude clouds. The winds here are powerful, driven by the temperature difference between the illuminated and dark hemispheres, and these winds carry the vaporized iron westward toward the cooler night side. As the vapor crosses into the cooler region, it condenses back into liquid droplets and falls from the sky as rain made of molten metal. You are looking at clouds that contain iron, and below them, the rain falls in glowing streams. The droplets cool as they descend, but they remain liquid until they reach lower atmospheric layers, where temperatures are high enough to keep them molten. The ground below, if it can be called ground, is battered by this continuous iron rain, and any surface features are constantly reshaped by the bombardment. The night side itself never sees the star directly, but the heat transported by atmospheric circulation keeps it far warmer than it would be otherwise. The star is a type F star, hotter and more massive than the Sun, and the planet orbits close enough to be tidally locked in place. From the surface of the day side, the star dominates the sky, unmoving and brilliant, while on the night side, the sky remains dark except for the faint glow of the iron rain, cooling as it falls. Astronomers detected the iron signature by analyzing starlight that passed through the planet's atmosphere during transits, and the presence of iron vapor was confirmed through spectroscopy. The discovery revealed that weather on exoplanets could involve materials that on Earth exist only as solids. You adjust your course and head toward another world where the rain is made not of metal, but of glass. You visited HD 189733b earlier from a distance, but now you descend closer to the atmosphere and enter the zone where the silicate clouds form. The winds hit your vessel immediately, buffeting the hull with forces far stronger than anything experienced in Earth's atmosphere. The instruments register wind speeds exceeding 8,700 kilometers per hour, and outside the viewport, the atmosphere is a blur of motion. The glass particles are microscopic, formed when silicate compounds condense at high altitude and then get caught in the jet stream that circles the planet. These particles are sharp, and they move with enough speed to erode any surface they contact. The deep blue color of the planet comes from the way these particles scatter light, similar to how Earth's sky appears blue but far more intense. The planet's atmosphere contains sodium, which adds to the blue hue, and the combination creates a world that looks deceptively beautiful from space. The temperature here is lower than on the Iron Rain world, around 1000 degrees Celsius, but the wind speed makes this planet far more dangerous. The glass moves in horizontal sheets, driven by the circulation between day and night, and the rain never falls vertically. If you could stand on the surface, protected somehow from the heat and wind, you would see the glass streaking past parallel to the ground, a sandblaster moving at hypersonic speeds. The surface below is scoured smooth by this endless abrasion, with no mountains or valleys able to form under such conditions. You leave the blue world and travel to HAT P7b, a planet where the clouds may be made of corundum. Corundum is aluminum oxide, the material that forms rubies and sapphires on Earth. And at the temperatures present on this planet, it can exist as vapor and condense into tiny crystals that drift through the atmosphere. The planet is roughly the size of Jupiter, and it orbits a star hotter than the Sun at a very close distance. The dayside temperature exceeds 2,600 degrees Celsius, and the night side is cooler, but still far too hot for familiar materials to remain solid. The winds on this planet do not blow in the direction astronomers initially expected. Observations revealed that the hottest point on the planet is not directly under the star, but is offset to one side, shifted by high-altitude winds that transport heat eastward. This wind pattern suggests strong atmospheric circulation, and the offset hotspot was one of the first weather features detected on an exoplanet. The corundum clouds form at high altitudes, where temperatures allow aluminum oxide to condense, and as these clouds drift through the atmosphere, they may release their crystals as rain. Imagine standing beneath a sky where rubies and sapphires fall from clouds, gemstones tumbling through air thick with heat and pressure. The rain would not be gentle, and the crystals would not survive the descent intact. But for a moment, high in the atmosphere, they exist as tiny particles of mineral, suspended in gas. The planet reflects a small amount of light back into space, and the measured albedo gives clues about cloud composition and atmospheric properties. The star, a type F star larger and brighter than the Sun, provides intense illumination, and the planet races around it in just over 2 Earth days. You move onward to a planet where the atmosphere has been mapped in more detail than almost any other exoplanet. Kepler 7b is a bloated gas giant with clouds that have been tracked and analyzed through changes in the light reflected from its surface. The planet is 1.5 times the size of Jupiter, but far less massive, making it extremely low in density. The clouds are bright, possibly made of silicate particles, similar to those on HD 189733b, but arranged in patterns that astronomers have been able to observe directly. The cloud patterns appear as bright and dark regions that shift as the planet rotates. The bright regions are likely high-altitude clouds that reflect more light, while the darker areas may be gaps where deeper, warmer atmospheric layers are visible. The fact that these patterns have been mapped represents a significant achievement in exoplanet observation. The techniques used involve measuring tiny changes in brightness as different parts of the planet rotate into and out of view, and the resulting maps show weather systems on a world hundreds of light years away. The atmosphere circulates in ways driven by temperature differences and the planet's rotation. The day side is significantly hotter than the night side, and this temperature gradient creates winds that transport heat and cloud material around the planet. The clouds themselves may condense and evaporate in cycles, forming on the cooler night side and dissipating on the hotter day side. The planet orbits its star every 5 days, and the rapid orbit means weather patterns shift quickly compared to the slow seasonal changes on Earth. You set course for a planet with a completely different kind of atmosphere. WASP 96b is a hot Jupiter with skies that are almost entirely clear, with no clouds or haze to block the view into the atmospheric depths. This clarity makes it an ideal target for studying atmospheric composition, and observations have revealed strong signatures of sodium, an element that is hidden by clouds on many other hot Jupiters. The planet is slightly larger than Jupiter and orbits a sun-like star every 3.4 days. The clear atmosphere suggests that conditions here do not favor cloud formation, possibly because the temperature and pressure combination keeps materials in vapor form rather than allowing them to condense. The lack of clouds means that starlight can penetrate deep into the atmosphere, and spectroscopy reveals details about chemical composition that would be obscured on cloudier worlds. Sodium is abundant, and its presence creates a strong absorption feature in the spectrum of light that passes through the atmosphere during transits. From the upper atmosphere, you would have an unobstructed view downward into the deeper layers, where temperature and pressure increase steadily. The sky would not show the haze or clouds familiar from Earth or from other gas giants, just a gradual transition from thin upper layers to denser lower regions. The star shines bright and close, and the planet receives intense radiation that keeps the atmosphere hot and prevents condensation. The clarity here is unusual, and it makes this planet valuable for scientific study, even as it represents a different kind of atmospheric extreme. You turn toward HD 80606b, a planet with an orbit so elliptical that it experiences rapid and extreme temperature changes. The orbit carries the planet far from its star and then swings it close in a trajectory that resembles a comet more than a typical planetary path. During the closest approach, the planet heats up by 700 degrees Celsius in only 6 hours, a temperature spike so rapid that the atmosphere barely has time to respond. The sudden heating creates shock waves and possibly supersonic winds as the atmosphere tries to redistribute the energy. The planet is roughly 4 times the mass of Jupiter, and the eccentric orbit takes it from a relatively cool distance to a scorching close approach, and back again every 111 days. Astronomers have observed the heating event directly by monitoring infrared radiation from the planet, and the data shows the temperature rising sharply as the planet makes its closest pass by the star. The atmosphere on the day side is blasted with radiation during perihelion, and then the planet swings away and the temperature drops again. This extreme variation means the planet never reaches equilibrium. The weather is in a constant state of response to changing conditions, and atmospheric models suggest that massive storms may form and dissipate with each orbital cycle. The winds generated by the rapid heating could reach speeds that exceed anything on the other planets you have visited, driven by the sudden energy input and the attempt to move heat from the day side to the night side. The surface, if there is anything that could be called a surface, below the thick atmosphere, experiences conditions that swing from extreme to even more extreme with each orbit. You move away from the elliptical giant and approach K2, 141b, a planet where the atmosphere itself is made of vaporized rock. The planet is slightly smaller than Earth, and it orbits its star at a distance so close that the surface reaches temperatures high enough to turn rock into gas. The day side is covered in a magma ocean that extends across 2/3 of the planet, and above this molten surface, rock vapor rises into the atmosphere and forms clouds made of minerals. The clouds drift with the wind toward the night side, where temperatures drop enough for the rock vapor to condense. It falls as rain, but instead of water droplets, the rain consists of tiny particles of solidified rock. This rain accumulates on the night side, and over time, the material flows back toward the day side through subsurface currents, where it melts again and evaporates to continue the cycle. The planet has a weather system driven by rock instead of water, and the entire surface is locked in this continuous loop of evaporation and precipitation. The magma ocean glows red and orange in the starlight, and the surface is never solid. Temperatures reach 3,000 degrees Celsius on the day side, and the night side, while cooler, is still hot enough to keep rock molten in many areas. The planet is tidally locked, and the star hangs in the same position in the sky forever, pouring energy onto the molten surface and maintaining the conditions that keep the rock vapor cycle active. Observations have detected evidence of this rock vapor atmosphere through spectroscopy, revealing absorption features consistent with vaporized minerals. You leave the rock vapor world and head toward COROT 7b again, this time focusing on the weather patterns. You visited this planet earlier for its role as the first confirmed rocky exoplanet, but the weather here deserves closer attention. On the day side, rock evaporates into the atmosphere, just as it does on K2 141b, and the vapor is carried by winds toward the cooler night side. As the vapor cools, it condenses into liquid droplets that fall as rain, and if the cooling continues, the droplets solidify into pebbles before hitting the ground. The rain here could consist of molten rock droplets, solid pebbles, or a combination of both depending on altitude and temperature. Sodium and potassium vapor have been detected in the atmosphere, and these elements add to the exotic chemistry of the air above the surface. The planet's weather is driven entirely by the temperature difference between the permanent day and night sides, and the circulation patterns create a steady flow of material from hot to cool and back again through underground currents. The sky above the day side would glow with the heat of vaporized rock, and the night side sky might show faint streaks of light as molten droplets fall and cool during their descent. There is no blue sky here, no familiar clouds, just the glow of heat and the haze of mineral vapor. The surface itself shifts constantly, reshaped by the flow of molten material and the impact of solidified rain. Stability does not exist on this world, and every feature is temporary, erased, and reformed in the ongoing churn of heat and matter. Your journey through these weather systems has taken you from iron rain to glass storms, from gemstone clouds to rock vapor atmospheres. And each planet shows a different way that familiar materials can behave under extreme conditions. The weather on these worlds is not driven by water or familiar atmospheric gases, but by metals and minerals that exist in states Earth never experiences. Telescopes detect these phenomena through careful observation of starlight, measuring absorption lines and brightness changes that reveal chemical composition and atmospheric dynamics. The skies on these planets would look alien to any Earth-based observer, but they follow the same physical laws, just applied to materials and conditions far outside the range of terrestrial experience. As you leave the storm zones and prepare to move toward worlds locked in permanent configurations, the data you have gathered paints a picture of weather as a universal phenomenon, operating wherever temperature differences and atmospheric circulation exist, regardless of what substances make up the rain or clouds. You are approaching a planetary system that lies only 4.2 light-years from Earth, the closest exoplanet to our own world. Proxima Centauri b orbits a small red dwarf star, and as your vessel enters the system, the star appears dimmer and cooler than the Sun, glowing with a soft red light that gives everything a muted quality. The planet itself is slightly more massive than Earth, and it circles the star at a distance that places it within the habitable zone, the region where temperatures might allow liquid water to exist. But there is a complication, and you can see evidence of it as you approach the planet and notice that one hemisphere is always illuminated while the other remains in darkness. The planet is tidally locked to its star. The same gravitational forces that lock our moon to always show one face toward Earth have locked this planet so that one side perpetually faces Proxima Centauri, while the other side never sees the star at all. The day side receives constant radiation, and the night side is frozen in endless darkness. Between these two extremes lies the terminator zone, the boundary region where day meets night, and it is here that conditions might be temperate enough for liquid water to pool and persist. You descend toward the terminator, and the view splits into two distinct halves. On one side, the red dwarf hangs low on the horizon, casting long shadows and bathing the landscape in dim, crimson light. On the other side, darkness stretches away into a night that has lasted for billions of years. The temperature difference between these regions is extreme, with the day side possibly reaching temperatures above the boiling point of water, and the night side dropping far below freezing. If the planet has an atmosphere, and scientists think it might, then winds would blow constantly from the hot side toward the cold side, trying to equalize the temperature, but never succeeding. The terminator zone is a narrow band, perhaps only a fraction of the planet's total surface, but it represents the only region where temperatures might remain stable enough for liquid water. If you could stand here, you would see the star perpetually on the horizon, never rising or setting, just sitting at the edge of the world and providing a steady source of dim light. The ground beneath your feet might be wet with water transported by atmospheric circulation, and the sky above might show clouds formed from vapor carried across the boundary from the hotter regions. Proxima Centauri itself is a red dwarf, a type of star far smaller and cooler than the Sun. Most stars in the galaxy are red dwarfs, and many of them host planets in close orbits. Because the stars are cool, the habitable zone lies much closer to the stellar surface than it does around Sun-like stars, and this close proximity increases the likelihood of tidal locking. Proxima Centauri b orbits its star every 11 days, a rapid orbit that keeps the planet in a tight gravitational embrace. The star is known to produce flares, sudden bursts of radiation that could strip away atmospheric gases over time. And whether the planet has managed to retain an atmosphere remains uncertain. You leave Proxima Centauri b and travel 39 light-years to a system that contains not one, but 7 tidally locked planets. The TRAP-PIST-1 system appears ahead, and the star at its center is even smaller and cooler than Proxima Centauri, classified as an ultra-cool dwarf. The 7 planets orbit so close to the star that all of them would fit within the distance between the Sun and Mercury, and all 7 are likely locked with one face always toward the star. You approach TRAP-PIST-1e, the 4th planet from the star, and one of the most Earth-like in size and position. The planet is slightly smaller than Earth, and it orbits within the habitable zone, where surface temperatures might allow liquid water to exist. As you enter orbit, the familiar pattern of permanent day and night becomes visible. The day side is bathed in the dim red glow of the ultra-cool dwarf, and the night side remains dark, except for whatever faint light might be reflected from neighboring planets. The TRAP-PIST-1 system is compact, and from the surface of Planet E, the other planets would be visible in the sky, some of them appearing larger than the Moon does from Earth. The entire system is gravitationally linked, with the planets tugging on each other in a complex dance of orbital resonances. These resonances help stabilize the orbits and prevent the planets from crashing into each other, and they also provide a way for astronomers to measure planetary masses through careful observation of orbital timing. You descend toward the terminator of TRAP-PIST-1e, and the landscape here might resemble the twilight zone on Proxima Centauri b. The star sits on the horizon, unmoving, and the temperature in this region is thought to be moderate enough for liquid water. If the planet has an atmosphere, it would redistribute heat through winds and weather, and the twilight band might be broader and more hospitable than on a planet without air. Scientists have used models to simulate atmospheric circulation on tidally locked planets, and the results suggest that even a thin atmosphere can significantly widen the habitable region. The star itself is incredibly dim compared to the Sun, putting out only a fraction of a percent of the solar energy output. From the surface of Planet E, the star would appear larger than the Sun does from Earth because of the close orbital distance, but it would glow with a deep red color and the light would feel weak. Plants on such a world, if any existed, would need to adapt to the low light levels and the specific wavelengths provided by the red dwarf. The entire system is young in terms of human discovery, having been found only in recent years, and it represents one of the best opportunities to study potentially habitable worlds around small stars. You leave the TRAP-PIST-1 system and travel to LHS 1140b, a super-Earth that orbits a red dwarf star 40 light-years from Earth. The planet is about 1.4 times Earth's radius and 6.6 times more massive. making it dense and likely rocky. It orbits within the habitable zone, and like the other worlds you have visited in this part of the journey, it is almost certainly tidally locked to its star. The day side receives radiation from the red dwarf, and the night side remains in perpetual shadow. The density of this planet suggests a composition rich in rock and iron, and the strong gravity would make standing on the surface a heavy experience. If you could somehow stand on the day side, the red dwarf would hang motionless in the sky, smaller and dimmer than the sun, but close enough to provide warmth. The night side would be frozen, with temperatures dropping far below anything Earth experiences, and the only hope for liquid water would lie in the terminator zone, or in the possibility of a thick atmosphere that could transport heat efficiently. Observations of LHS 1140b have revealed that the star is quieter than many red dwarfs, producing fewer flares and less radiation variability. This relative calm increases the chances that the planet has retained an atmosphere over its lifetime, and it makes the world a promising candidate for future study. Astronomers hope to analyze the planet's atmosphere using advanced telescopes, looking for signs of water vapor or other molecules that might indicate habitable conditions. You travel next to GJ 1132b, a rocky planet about 1.2 times Earth's radius that orbits a red dwarf star 39 light-years away. This planet is tidally locked, and it orbits its star every 1.6 Earth days, a rapid orbit that keeps it very close to the stellar surface. The proximity means the planet is likely too hot to support life as we know it, but recent observations have detected evidence of an atmosphere, which is surprising given the intense radiation the planet receives. The atmosphere appears to be a secondary atmosphere, formed not during the planet's initial creation, but later through volcanic outgassing or other processes. The planet may have started with a thick hydrogen envelope that was stripped away by radiation, and the current atmosphere could be made of heavier gases released from the interior. The detection of this atmosphere makes GJ 1132b interesting, because it suggests that even planets subjected to harsh radiation can maintain or regenerate atmospheres under certain conditions. From the surface of the day side, the red dwarf would dominate the sky, and the ground would be hot enough to glow faintly in the darkness. The night side would be cooler, and if the atmosphere is thick enough, winds would blow continuously from day to night, creating weather patterns driven entirely by the temperature gradient. The planet's surface is probably rocky, with no oceans or large bodies of water, and the landscape would be barren and shaped by volcanic activity and thermal stress. You set course for Kepler 442b, a planet that is 1.3 times Earth's radius and orbits in the habitable zone of an orange dwarf star. The star is smaller and cooler than the Sun, and the planet orbits close enough that tidal locking is likely. The orbital period is 112 days, longer than most of the tidally locked worlds you have visited, and this longer period might allow for some rotational motion, though most models suggest the planet is locked in place. The planet has a 62% chance of being rocky based on its size and mass estimates, and if it has an atmosphere, the conditions on the terminator might be conducive to liquid water. The star is stable and long-lived, and the planet has likely been in its current orbit for billions of years. providing time for any potential atmosphere to stabilize and for surface conditions to reach equilibrium. The day side would receive steady illumination from the orange star, and the night side would remain dark with the familiar division between heat and cold. You finish your tour of tidally locked worlds by visiting Ross 128b, a planet only 11 light-years from Earth that orbits one of the quietest red dwarfs known. The planet is about 1.4 times Earth's mass, and it orbits in the habitable zone with a period of 9.9 days. The star produces very few flares, which makes this one of the most stable environments among red dwarf systems. And the planet's proximity to Earth makes it a high-priority target for future observations. The planet is almost certainly tidally locked, and the terminator zone here might be one of the most temperate regions you have encountered. The star's low activity means the planet has a better chance of retaining an atmosphere and maintaining stable surface conditions over long periods. From the terminator, the star would sit on the horizon, glowing with a soft red light, and the temperature might be cool but not freezing, warm but not scorching. If water exists here, it could pool in lakes or seas along the twilight band, and the sky might show clouds drifting in the steady winds. The tidal locking that defines all these worlds creates a kind of permanence that is alien to Earth's experience. On Earth, the sun rises and sets, seasons change, and every location experiences both day and night over the course of a year. On these locked worlds, the star never moves, the sky never changes, and the division between light and dark is absolute and eternal. The terminator zones represent narrow refuges, places where the extremes are balanced and where conditions might, just might, allow for the presence of liquid water and the possibility of something more. As you leave the last of the tidally locked planets and prepare to move towards worlds dominated by water, the unchanging skies fade behind you, replaced by the deeper darkness of space and the anticipation of oceans without end. You are descending toward a planet covered entirely in water, a world where no land breaks the surface and the ocean extends uninterrupted from pole to pole. GJ 1214b lies 48 light-years from Earth, and as your vessel approaches, the planet appears wrapped in a thick haze that obscures any view of the surface below. The haze is likely water vapor, steam rising from a global ocean and condensing into a dense atmospheric envelope that traps heat and maintains temperatures far above what Earth's oceans experience. The planet is about 2.6 times Earth's radius, and it is roughly 6.5 times more massive. You enter the upper atmosphere, and the haze thickens around you. The temperature rises steadily as you descend, and the pressure increases with every kilometer. There is no solid ground waiting below, just water in various states, from vapor in the upper atmosphere to liquid in the deeper layers, and possibly exotic forms of ice at extreme depths. The ocean here is not like Earth's oceans, which cover 70% of the surface and average a depth of about 4 kilometers. This ocean could be hundreds of kilometers deep, extending down until the pressure becomes so great that water transforms into states that do not exist naturally on Earth. The planet orbits a red dwarf star every 38 hours, close enough that it is likely tidally locked. The day side receives constant starlight, and the ocean there is warmed by the radiation, creating convection currents that circulate heat through the water. The night side is cooler, and the temperature difference drives global ocean currents that move vast quantities of water from one hemisphere to the other. If you could dive below the surface, you would find layers of water at different temperatures and densities, stratified by depth and location, with the deepest layers under such immense pressure that the water behaves in ways unfamiliar to surface chemistry. At extreme depths, the pressure could compress water into a form called hot ice, where the molecules are locked into a solid crystalline structure, despite temperatures that would normally keep water liquid. This ice is not cold, it is hot, and it forms not because of low temperature, but because of high pressure. The ocean floor, if it can be called that, might consist of a layer of this exotic ice, sitting atop a rocky core, and above it, hundreds of kilometers of liquid water extending up toward the steamy atmosphere. The planet is sometimes described as a watermelon, in terms of density, heavier than a gas giant, but lighter than a purely rocky world, and the comparison suggests a composition dominated by water. You leave GJ 1214b and travel to K2 18b, a planet that made headlines when water vapor was detected in its atmosphere. The planet is about 2.6 times Earth's radius and 8 times more massive, and it orbits a red dwarf star 124 light-years away. The orbital period is 33 days, and the planet sits within the habitable zone, receiving roughly the same amount of radiation from its star as Earth receives from the Sun. The atmosphere is thick and rich in hydrogen, and within it, water vapor has been confirmed through spectroscopic observations. The discovery of water vapor in the atmosphere of a planet in the habitable zone represents a significant milestone in exoplanet research. Water is essential for life as we know it, and finding it in the atmosphere of a potentially habitable world suggests that conditions there might support liquid water on the surface or within cloud layers. The planet is not a twin of Earth. It is much larger and more massive, and the thick hydrogen atmosphere makes it quite different from our own world. But the presence of water vapor adds to the possibility that this planet could have oceans or water in some form. You descend toward K2 18b, and the atmosphere grows thick around you. The hydrogen is the dominant gas, but water vapor is present in measurable amounts, and clouds likely form in regions where temperature and pressure allow condensation. The planet may have a rocky core beneath the thick atmosphere, or it could be more similar to a mini Neptune with a small core and a deep gas envelope. The exact structure remains uncertain, but the presence of water vapor opens the possibility that deeper in the atmosphere, or on the surface, liquid water might exist. From the upper atmosphere, the red dwarf star is visible, smaller and cooler than the Sun, but providing steady illumination. The planet is not tidally locked because of its longer orbital period, so day and night cycle in a rhythm that repeats every 33 Earth days. The rotation period is unknown, but if the planet rotates at a reasonable rate, the day-night cycle could create weather patterns, with clouds forming and dissipating as the surface heats and cools. The atmosphere circulates, driven by temperature differences and the planet's rotation, and water vapor moves through this circulation, condensing into clouds and possibly falling as rain in some regions. You leave K2-18b and head toward Kepler-22b, a planet that was one of the first confirmed exoplanets discovered within the habitable zone of a Sun-like star. The planet is about 2.4 times Earth's radius, and it orbits its star every 290 days, a period close to Earth's year. The star is slightly smaller and cooler than the Sun, and the planet receives about 25% less energy than Earth does, which places it on the cooler edge of the habitable zone. If the planet has a thick atmosphere with greenhouse gases, surface temperatures could be warm enough for liquid water. The composition of Kepler-22b is unknown. It could be a rocky super-Earth with a thick atmosphere, or it could be a water world with a global ocean, or it might be a mini Neptune with no solid surface at all. The size suggests it is too large to be purely rocky, and models favor either a water-rich composition or a planet with a substantial gas envelope. If it is a water world, the ocean could cover the entire surface, and the depth might extend for many kilometers before reaching a solid core or a layer of high-pressure ice. You approach the planet, and from orbit it appears featureless, wrapped in clouds or haze that hides the surface. The atmosphere could contain water vapor, and if the surface is covered in ocean, evaporation would maintain a humid atmosphere, with clouds forming and dissipating in weather patterns. The temperature on the surface, assuming there is a surface, might be temperate, cool but not freezing, and if greenhouse gases are present, the climate could be stable enough for liquid water to persist over geological timescales. The star shines with a yellowish light, similar to the Sun, and from the surface the sky might look familiar, though the star would appear slightly smaller and dimmer. The planet's year is long enough that seasons could occur if the planet has an axial tilt, and the changing angle of sunlight would create variations in temperature and weather. If oceans exist, currents would circulate heat around the planet, moderating the climate and creating a more uniform temperature distribution than a planet without water. You set course for TOI 700d, an Earth-sized planet in the habitable zone of a red dwarf star. The planet is about 1.2 times Earth's radius, and it orbits every 37 days at a distance that places it within the range where liquid water could exist. The star is small and cool, only about 40% the mass of the Sun, and the planet orbits close enough that it might be tidally locked, though the evidence is not conclusive. If the planet has an atmosphere, it could redistribute heat and widen the habitable region. You descend toward the planet, and the surface comes into view, though details remain scarce because the planet is difficult to observe from Earth. The presence of an atmosphere is possible but not confirmed, and whether water exists on the surface remains an open question. The planet's size suggests it could be rocky, and if it has water, it might exist as oceans, ice caps, or subsurface reservoirs. The red dwarf star provides dim illumination, and from the surface, the light would have a reddish tint, casting the landscape in colors unfamiliar to Earth-based life. The planet is one of the few Earth-sized worlds discovered in the habitable zone of a nearby star, and it represents a target for future study. Telescopes capable of analyzing atmospheric composition could determine whether water vapor is present, and over time, Observations might reveal whether this world is truly habitable, or if it is too dry, too hot, or too cold to support liquid water. For now, it remains a candidate, a world that might have oceans or might be barren, and the uncertainty makes it both intriguing and frustrating. You turn back toward a planet you visited earlier in a different context. Gliese 436b is a Neptune-sized world that orbits a red dwarf star, and it is known for having water in a state that does not exist on Earth. The planet is about 4 times Earth's radius and roughly 23 times more massive, and it orbits very close to its star, completing one orbit every 2.6 days. The surface temperature reaches 439 degrees Celsius, hot enough to boil water at Earth pressures. But the pressure on this planet is so extreme that water cannot boil. You descend into the atmosphere, and the pressure builds rapidly. Below the gaseous outer layers, the temperature and pressure combine to create conditions where water is forced into a solid state despite the heat. This solid water is not ice in the familiar sense. It is a high-pressure form known as hot ice. And it exists because the pressure crushes the water molecules into a crystalline structure, even though the temperature is far above the freezing point. The planet is thought to have a core of rock surrounded by a thick mantle of this exotic ice. And above the ice, a layer of water and other volatiles extends up into the atmosphere. The concept of burning ice seems contradictory, but it is a natural consequence of extreme pressure. On Earth, water transitions from solid to liquid to gas based on temperature, but at high pressures, the phase diagram changes, and water can remain solid at temperatures that would normally vaporize it. Gliese 436b exists in this high-pressure regime, and the water in its interior is locked into a state that combines the structure of ice with the temperature of steam. The planet's surface, if it has one, would be hidden beneath this mantle, and the conditions there would be hostile to any form of life known to exist. You leave the hot ice world and travel to GJ 367b, a planet that is not dominated by water, but by iron. The planet is about 70% the size of Earth, but nearly 60% more massive, giving it a very high density that suggests a composition rich in metal. The planet orbits a red dwarf star every 8 hours, one of the shortest orbital periods known, and the proximity to the star means surface temperatures exceed 1,500 degrees Celsius. The planet is likely the exposed core of a larger world, stripped of its outer layers by the intense radiation and heat. The surface here is not covered in water or ice, but in molten metal and rock. The high density indicates that iron and other heavy elements dominate the composition, and the planet may represent what is left after a gas giant lost its atmosphere, or after a collision stripped away the lighter materials. The ground beneath you, if you could stand on it, would be a sea of lava mixed with liquid iron, glowing red and orange in the starlight. There are no oceans here, no water vapor, just the bare remnants of a planetary core, exposed to the harshness of space. The contrast between the water worlds and this metallic remnant highlights the diversity of planetary compositions. Some worlds are rich in volatiles, covered in water, or wrapped in thick atmospheres of hydrogen and steam. Others are stripped down to their densest components, their surfaces barren, and their interiors dominated by iron and rock. The presence or absence of water shapes the character of a planet, determining whether it is a steamy greenhouse, a frozen ice shell, or a barren core glowing with residual heat. As you move away from GJ 367b and leave the water worlds behind, the memory of endless oceans and steamy atmospheres lingers. These planets show that water, the substance essential to life on Earth, exists in many forms across the galaxy, from global oceans hundreds of kilometers deep to exotic ice compressed by crushing pressure. Some of these worlds might host life, though the conditions are often extreme and the environments hostile. Others are simply remarkable examples of how common molecules behave under uncommon circumstances. The search for habitable worlds often focuses on the presence of water, and these planets represent a range of possibilities, from temperate oceans beneath breathable skies to hellish steam baths and high-pressure ice mantles. The journey continues, and ahead lie worlds that wander without stars, orphaned and alone in the darkness of space. You are drifting through a region of space, far from any star, and ahead of you, a planet moves silently through the void. There is no sun to illuminate its surface, no parent star to provide warmth or light. This is PSO J318.5, a rogue planet that has been wandering through the galaxy alone for millions of years. The planet is about 6.5 times the mass of Jupiter, and it glows faintly with infrared radiation, heat left over from its formation. You approach slowly, and the planet appears as a dim red sphere against the blackness, barely visible even with your instruments. The surface temperature is around 800 degrees Celsius, far cooler than the scorching worlds you visited earlier, but still hot enough to glow in the infrared spectrum. The heat comes from the interior, where the planet is slowly contracting and releasing gravitational energy. There is no external source of warmth, no star to heat the atmosphere, and over billions of years, the planet will cool further until it becomes a dark, frozen object drifting silently through space. For now, it retains enough heat to be detected, and astronomers discovered it through direct imaging, capturing the faint glow without needing to observe it passing in front of a star. You descend toward the upper atmosphere, and the darkness around you is absolute. There are stars in the distance, but they are so far away that they provide no meaningful light. The planet is alone, and the sky from its surface would show only the faint backdrop of the Milky Way. No bright sun, no nearby stellar companion. If you could stand on the surface, assuming there is a solid surface beneath the thick atmosphere, you would experience a world lit only by its own internal heat, a dim red glow rising from below and fading into the darkness above. Rogue planets like this one are thought to form in one of two ways. They might begin as part of a planetary system and then be ejected through gravitational interactions with other planets or passing stars. Alternatively, they could form independently in regions of space where gas and dust collapse under their own gravity, similar to the way stars form, but without enough mass to ignite nuclear fusion. PSO J318.5 is young, only about 23 million years old, and it still retains heat from its formation, which makes it easier to detect than older, cooler rogues. You leave the glowing rogue and travel to another wandering world. CFBDSIR 2149 is a planetary mass object that drifts through space without a star, located about 100 light-years from Earth. The object is about 4 to 7 times the mass of Jupiter, and its surface temperature is around 400 degrees Celsius, cooler than PSO J3 18.5, but still warm enough to emit infrared radiation. The planet is older, and it has cooled more, but it still glows faintly in the darkness. The object was discovered as part of a survey looking for brown dwarfs, objects that are too massive to be planets, but not massive enough to sustain hydrogen fusion like stars. CFBD SIR 2149 sits on the boundary between planet and brown dwarf, and its classification depends on how it formed. If it formed in a protoplanetary disk around a star and was later ejected, it is a rogue planet. If it formed independently from a collapsing cloud of gas, it might be considered a brown dwarf. The distinction is subtle, and it highlights the difficulty of categorizing objects that exist in the gray area between planets and stars. You approach the object, and from close range, it appears similar to PSO J3 18.5, a dark sphere with a faint reddish glow. The atmosphere is thick, and clouds might form in the upper layers, though without a star to drive weather patterns, the atmospheric circulation is powered entirely by the planet's internal heat. The winds would be slow compared to the hypersonic gales on hot Jupiters, and the weather would be dominated by convection, rising from the warm interior and cooling in the upper atmosphere before sinking again. You set course for the coldest known planetary mass object drifting free in space. Y0855 is only 7.2 light-years from Earth, making it one of the closest known objects of its type. The surface temperature is estimated to be between -13 and -10 degrees Celsius, barely below the freezing point of water, and far colder than any other free-floating object discovered. The planet is about 3 to 10 times the mass of Jupiter, and it is so cold that water ice clouds might form in its atmosphere, the first time such clouds have been detected outside our solar system. You descend into the frigid atmosphere, and the temperature drops steadily. The darkness here is profound, and the only light comes from the faint heat of the planet itself, not enough to create a visible glow, but detectable with infrared instruments. The water ice clouds drift through the upper atmosphere, suspended in air composed mostly of hydrogen and helium. The clouds are similar in composition to the ice clouds on Jupiter, but the temperatures here are much colder, closer to Earth's polar regions than to the interiors of gas giants. The planet is old, possibly billions of years in age, and it has cooled to the point where it barely radiates any heat. Detecting it required sensitive infrared telescopes, and even then it appears as only a faint smudge in the data. The atmosphere is stable, with no star to heat it or strip it away, and the planet will continue drifting through space, cooling slowly over eons, until it becomes indistinguishable from the background cold of interstellar space. The water ice clouds are a reminder that even in the coldest, darkest corners of the galaxy, familiar materials can exist in forms that echo those on Earth. You leave Y0855 and travel to a rogue planet with a powerful magnetic field. SIMP J0136, known for the rest of the journey as the magnetic rogue, is about 12.7 times the mass of Jupiter, right at the boundary between planet and brown dwarf. The object has a magnetic field far stronger than Jupiter's, and it generates radio emissions that can be detected from Earth. These emissions are thought to be caused by interactions between the magnetic field and charged particles in the atmosphere, creating auroras similar to the northern and southern lights on Earth, but far more intense. You approach the magnetic rogue, and your instruments register the strength of the magnetic field. The field extends far into space around the planet, and if solar wind existed here, it would interact with the field to create spectacular auroras. But there is no solar wind in interstellar space, and the auroras are instead powered by the planet's rotation and the movement of charged particles within the atmosphere. The radio emissions flicker and pulse as the planet rotates, sweeping the magnetic field through space like a lighthouse beam. The surface temperature is around 800 degrees Celsius, similar to PSO J3 18.5, and the planet glows faintly with infrared light. The magnetic field is a feature that sets this rogue apart from others, and it suggests active processes in the interior, possibly a molten core that generates the field through dynamo action. The planet rotates rapidly, and the combination of rotation and internal heat drives the magnetic activity that makes the object detectable across light years. You turn your attention to a very different kind of wandering world. 2MA SSJ 2126 is a planet that orbits a star, but the distance is so vast that it was initially thought to be a rogue. The planet is about 11 to 15 times the mass of Jupiter, and it orbits its host star at a distance of roughly 1 trillion kilometers. The orbital period is approximately 900,000 years, and the star is so far away that it appears as just another point of light in the sky, indistinguishable from the background stars without careful observation. You approach the planet, and from its surface, the host star is barely brighter than the other stars scattered across the sky. The gravitational bond between planet and star is real but tenuous, and the planet experiences almost no heat or light from its distant sun. The environment here is similar to that of a true rogue, with the planet cooling slowly and relying on internal heat to maintain any warmth at all. The discovery of this extreme orbit challenged ideas about how far planets can exist from their stars, and it raises questions about the stability of such systems over billions of years. The planet is thought to have formed much closer to its star and then been scattered outward by gravitational interactions, possibly with other planets that have since been ejected or fallen into the star. The wide orbit places the planet in a region where it is vulnerable to gravitational perturbations from passing stars, and over time it might be pulled free entirely, becoming a true rogue wandering through the galaxy. For now it remains bound, but the connection is fragile, and the planet's future is uncertain. You leave 2MA SSJ 2126 and travel to a planetary system that survived an event so violent it should have destroyed everything. PS R1257 plus 12 is a pulsar, the rapidly spinning remnant of a star that exploded as a supernova, and it is orbited by at least 3 planets. The pulsar rotates hundreds of times per second, and it emits beams of radiation that sweep through space like a lighthouse. The planets were discovered through careful timing of the pulsar's pulses, which are affected by the gravitational pull of the orbiting worlds. You approach the system cautiously. The radiation here is intense, and the pulsar bathes everything in high-energy particles and electromagnetic waves. The planets orbit close to the pulsar, and they are subjected to conditions that would sterilize any surface. The inner planet is only about twice the mass of the Moon, and it orbits every 25 days. The second and third planets are roughly 4 times the mass of Earth, and they orbit in a configuration that suggests they formed after the supernova, possibly from debris left behind when the star exploded. The planets are dark, with no atmosphere and no internal heat. The pulsar provides no warmth, only radiation, and the surface of each planet is cold and barren. The pulsar's beam sweeps past at regular intervals, and if you could stand on one of these worlds, you would see the beam flash overhead like a strobe light, a reminder of the dead star's relentless rotation. These planets were the first exoplanets ever discovered, found in 1992, and they opened the field of exoplanet research by proving that planets could exist in extreme environments around stars very different from the Sun. You move away from the pulsar and consider the population of rogue planets in the galaxy. Estimates suggest there could be billions of rogue planets wandering through the Milky Way, possibly outnumbering stars. Most of them are too cold and dark to detect, and they drift silently through space, invisible except when they pass in front of a background star and create a brief gravitational lensing event. Some rogues retain heat from formation, and these can be detected through infrared surveys, but the majority are frozen and dark, remnants of planetary systems that experienced violent interactions and ejected their members into the void. The rogue planets you have visited represent a small sample of this vast population. Some are young and warm, glowing with the heat of recent formation. Others are old and cold, barely distinguishable from the background temperature of space. Some have powerful magnetic fields and active atmospheres, while others are frozen and inert. A few orbit stars at such great distances that they are almost indistinguishable from true rogues, and some orbit pulsars bathed in radiation and locked in orbits around dead stars. Each one tells a story of formation, ejection, or survival, and together they reveal that planetary systems are dynamic and sometimes violent places where not every planet remains in its birth orbit. As you leave the dark regions of space and prepare to return to systems where stars provide light and warmth, the memory of these lonely worlds stays with you. The silence of space is profound here, far from any star, and the planets drift through the darkness without witness, their surfaces cold or faintly glowing, their skies empty of any sun. They are orphans, wanderers, survivors, and mysteries, and they exist in numbers that suggest the galaxy is filled not only with planets that orbit stars, but also with planets that roam free, untethered and alone. You are approaching a planet that should not exist according to early models of planetary formation. Kepler-10c is a super-Earth with a mass 17 times greater than our own world, and it is composed mostly of rock rather than gas. Planets this massive were thought to accumulate thick hydrogen envelopes and become gas giants, but Kepler-10c defied expectations and remained rocky. The planet is about 2.3 times Earth's diameter, and the density measurements confirm that rock and iron dominate the composition. The planet has been called a mega-Earth, and its discovery forced scientists to reconsider the upper limits of rocky planet formation. You descend toward the surface, and the gravity becomes immediately apparent. Standing here would feel like carrying more than twice your own weight, and every movement would require significant effort. The planet orbits a sun-like star every 45 days, and the close proximity means surface temperatures are too high for liquid water. The atmosphere, if one exists, would be thick and heavy, compressed by the intense gravity into layers far denser than Earth's air. Mountains on this world would be low and broad, unable to rise high because the gravity pulls everything down with relentless force. The planet's size and mass place it in a category that has no equivalent in our solar system. Earth is the largest rocky planet we know directly, and anything bigger becomes Neptune or Jupiter, worlds dominated by gas. Kepler-10c suggests that rocky planets can grow much larger under the right conditions, and its existence opens the possibility that mega-Earths are more common than previously thought. The formation of such a massive rocky world likely required a protoplanetary disk rich in solid materials, and the planet would have needed to form quickly before gas giants in the system could scatter or consume the available rock and metal. You leave the mega-Earth and travel to a planet that represents the opposite extreme in density. WASP 107b is a gas giant with a radius close to Jupiter's, but a mass only about 10% as large. The density is so low that the planet has been compared to cotton candy, and it is one of the least dense planets ever discovered. The planet is extremely puffy, with a thick atmosphere that extends far into space, and very little solid or liquid material in the core. You enter the upper atmosphere, and the descent is unlike anything you have experienced on denser worlds. The atmosphere is mostly hydrogen and helium, and as you move deeper, the pressure increases so gradually that there is no clear boundary between layers. The temperature rises slowly, and the atmosphere remains gaseous for hundreds of kilometers. The planet orbits a sun-like star every 5.7 days, and the close proximity heats the atmosphere, causing it to expand and puff up even more than it would around a cooler or more distant star. The planet's low density suggests that the core is very small, possibly only a few times the mass of Earth, and the vast majority of the planet's volume is made up of extended atmosphere. The gravity at the upper levels is weak, and gas is slowly escaping into space, blown away by the stellar wind. Over time, the planet may lose a significant portion of its atmosphere, and it could eventually become smaller and denser, though this process takes millions of years. You leave WASP 107b and head toward a system with 3 super-puff planets, all of them exceptionally low in density. Kepler 51b, C, and D orbit a sun-like star, and all 3 have densities lower than any planet in our solar system. The planets are similar in size to Neptune, but far less massive, and their atmospheres are so extended that they resemble balloons more than solid objects. The system is young, only a few 100 million years old. and the planets may still be in the process of losing their extended atmospheres. You approach Kepler 51b, the innermost of the three superpuffs. The planet orbits every 45 days, and the atmosphere is thick with hydrogen and helium. Clouds likely form in the upper layers, though the composition of these clouds is uncertain. The planet is so diffuse that descending through the atmosphere would take a long time before reaching any region dense enough to resemble the interior of Jupiter or Saturn. The extended atmosphere makes the planet appear larger than it is, and the actual core may be relatively small, surrounded by thousands of kilometers of gas. The three planets in the Kepler 51 system are thought to be losing mass through atmospheric escape, and in the future, they may contract and become more typical Neptune-sized worlds. The low density suggests they formed farther from the star and then migrated inward, and the migration may have occurred before the protoplanetary disk dissipated, allowing the planets to retain their thick hydrogen envelopes. The system provides a glimpse of what planets look like in their youth, before stellar radiation and atmospheric escape have had time to reshape them. You leave the superpuffs and travel to TOI 849b, a planet that is almost entirely core with little or no atmosphere. The planet is about 3.4 times Earth's radius and roughly 40 times more massive, making it one of the densest exoplanets known. The density suggests the planet is made of rock and iron, and it likely represents the exposed core of a gas giant that lost its atmosphere through some violent process. The planet orbits a sun-like star every 18 hours, and the extreme proximity means surface temperatures exceed 1,500 degrees Celsius. You descend toward the surface, and the heat is intense. The ground below is likely molten, with lava covering much of the surface and glowing red in the starlight. The planet may have started as a gas giant similar to Jupiter, but interactions with the protoplanetary disk or with other planets could have stripped away the outer layers, leaving only the dense core behind. Alternatively, the planet could have formed close to the star and never accumulated a significant atmosphere, because the stellar radiation prevented gas from condensing onto the core. The surface gravity is strong, and the planet's composition is similar to what scientists think lies at the center of Jupiter or Saturn, deep below the thick atmospheres. Observing TOI 849b provides a rare opportunity to study the interior structure of gas giants without needing to peer through thousands of kilometers of gas. The planet is a naked core, and its existence challenges models of how planets retain or lose their atmospheres over time. You turn toward K2 141b, a planet you visited earlier in the context of weather, but now you focus on its strange physical structure. The planet is about 1.5 times Earth's radius, and it orbits so close to its star that the surface is covered in molten rock. The day side reaches temperatures around 3,000 degrees Celsius, and the night side is cooler but still hot enough to keep rock in a partially molten state. The planet is tidally locked, and the magma ocean on the day side is a defining feature of its structure. The magma glows with heat, and above it, rock vapor rises into the atmosphere and forms clouds. The vapor is transported by winds to the night side, where it cools and condenses, falling as a rain of solidified particles. The rain accumulates on the night side, and over time the material flows back toward the dayside through subsurface currents, where it melts again and rejoins the magma ocean. The entire surface is locked in this cycle, and there is no solid ground anywhere, just molten rock in constant motion. The planet's density suggests a composition similar to Earth, with an iron core and a rocky mantle, but the extreme temperatures prevent any crust from forming. The surface is fluid, and the landscape changes continuously as magma flows and solidifies and melts again. The star dominates the sky on the day side, and the heat is unrelenting, maintaining the conditions that keep the planet in a molten state. This is a world where rock behaves like water, and the familiar solidity of stone is replaced by a surface that flows and churns like an ocean. You leave K2, 141b, and travel to HATP 1b, a bloated gas giant with a density similar to cork. The planet is about 1.4 times the radius of Jupiter, but only about half as massive, giving it a very low overall density. The planet orbits a sun-like star every 4.5 days, and the close proximity heats the atmosphere and causes it to expand. The planet is inflated beyond what would be expected from heating alone, and the exact mechanism that keeps it so puffed up remains uncertain. You enter the atmosphere, and the descent is slow and gradual. The air is thin at the upper levels, and the pressure increases gently as you move deeper. The planet's low density means the gravity is weak for such a large world, and gas escapes easily into space, blown away by the stellar wind. The interior may contain a small core, possibly made of rock or ice, but the vast majority of the planet is hydrogen and helium extending outward in a diffuse envelope. The planet's inflated state suggests ongoing heating from within, possibly through tidal interactions with the star, or through the absorption of stellar radiation deep in the atmosphere. The heat is deposited in the interior and causes the atmosphere to expand, and the process continues as long as the planet remains close to the star. Over time, the planet may lose mass and contract, but for now, it remains one of the puffiest known worlds, a giant ball of gas with very little substance. You move to KELT 11b, another puffy planet with even lower density. The planet is about 1.4 times Jupiter's radius, but only about 1/5 as massive, giving it a density of just 0.09 grams per cubic centimeter. Lower than any planet in the solar system, the planet orbits a star that is larger and cooler than the Sun, and the orbital period is 4.7 days. The star itself is evolving off the main sequence, beginning to expand into a subgiant, and the increased radiation may contribute to the planet's extreme inflation. You descend into the atmosphere, and the structure is similar to WASP 107b and HATP 1b, with a thick hydrogen envelope and very little core mass. The planet is so diffuse that it feels more like a cloud than a solid object, and the boundary between the planet and space is gradual rather than sharp. The gravity is weak, and atmospheric escape is ongoing, with hydrogen and helium streaming away into space at a measurable rate. The planet is losing mass, and in the future, it may shrink significantly as the outer layers are stripped away. The extreme puffiness of planets like KELT 11b and WASP 107b raises questions about how long such structures can remain stable. Stellar radiation heats the atmosphere and causes expansion, but at some point, the gravity becomes too weak to hold the gas, and the planet begins to lose mass rapidly. These planets may represent a transitional phase, worlds that are currently bloated but will eventually contract as they lose their extended envelopes. Observing them provides insight into the processes that shape planetary atmospheres and determine which planets retain thick gas layers and which become stripped down to their cores. You finish your tour of extreme sizes and densities by visiting WASP-17b, a planet you encountered earlier for its retrograde orbit, but now you focus on its physical structure. The planet is nearly twice the size of Jupiter, but only about half as massive, making it one of the largest known exoplanets by radius. The planet orbits a sun-like star every 3.7 days, and the retrograde motion adds another layer of strangeness to an already unusual world. You enter the atmosphere, and the size of the planet becomes apparent. The atmosphere extends outward for thousands of kilometers, and the descent through the layers is long and gradual. The planet's large size is thought to result from intense heating by the star, combined with the effects of the retrograde orbit, which may subject the planet to additional tidal forces. The interior structure is similar to other puffy giants, with a small core and a vast hydrogen envelope. But the retrograde orbit suggests a violent history involving gravitational interactions that flipped the planet's motion relative to the star's rotation. The planet's density is extremely low, and it is losing mass to space through atmospheric escape. The size makes it an easy target for observation, and astronomers have studied its atmosphere in detail, detecting water vapor, carbon monoxide, and other molecules. The planet is a laboratory for understanding how atmospheres behave under extreme inflation, and it challenges models of planetary structure by existing at the edge of what gravity can hold together. As you leave WASP-17b and move away from the extremes of size and density, the variety of planetary structures becomes clear. Some worlds are dense and massive, rocky cores with crushing gravity that holds everything close. Others are diffuse and extended, gas envelopes so thin that they barely hold together, inflated by heat and losing mass to space. The range between these extremes is vast, and planets exist at every point along the spectrum, from mega-Earths with 17 times Earth's mass to superpuffs with densities lower than styrofoam. Each planet's structure is shaped by its formation history, its distance from the star, and the interactions it has experienced over millions or billions of years. The journey continues, and ahead lie worlds that orbit not one star, but two or even more, their skies filled with multiple suns, and their orbits shaped by the complex gravitational dance of binary and triple star systems. You are entering a star system where two suns orbit each other, and a planet circles both of them. Kepler-16b was the first confirmed circumbinary planet, a world that experiences the double sunset made famous by science fiction, but discovered here in reality. The two stars are smaller than the Sun, one an orange dwarf and the other a red dwarf, and they orbit each other every 41 days. The planet orbits both stars from a distance, completing one circuit every 229 days. As you approach, both stars are visible, separated by a distance similar to that between the Sun and Mercury, and the planet moves in a wide orbit around the binary pair. You descend toward the planet, and the surface temperature is well below freezing. The planet is similar in size to Saturn, and it is likely a gas giant with no solid surface to stand on. The two stars provide less combined light than the Sun, and the planet orbits far enough away that it receives only a fraction of the energy Earth gets from our single star. The atmosphere is cold, and clouds likely form in the upper layers, composed of materials that condense at low temperatures. From the upper atmosphere, both stars are visible, one larger and brighter than the other, and they move across the sky together, never far apart. The gravitational dynamics of a circumbinary system are complex. The planet's orbit must be stable, despite the shifting gravitational pull from two stars that are themselves moving around a common center of mass. Kepler-16b orbits outside the region where gravitational interactions would destabilize its path, and the orbit is nearly circular, which helps maintain stability. The discovery of this planet showed that binary star systems can host planets in stable orbits, and it opened the possibility that circumbinary planets might be common in the galaxy. You watch the double sunset from the upper atmosphere. The larger star sets first, dropping below the horizon and casting long shadows across the cloud tops. The smaller star follows soon after, and the sky darkens as both suns disappear. The light from the two stars combines to create a unique color in the sky, neither the yellow of a sun-like star nor the pure red of a red dwarf, but a blend of orange and red that shifts as the stars move relative to each other. The night here is darker than on Earth because the combined light from both stars is weaker than the sun, and the stars themselves are cooler and dimmer. You leave Kepler-16b and travel to Kepler-47c, a planet in a system with two stars and three known planets. Kepler-47c is the outermost planet, and it orbits in the habitable zone, the region where temperatures might allow liquid water to exist if the planet were rocky and had an atmosphere. The planet is about 4.7 times Earth's radius, making it too large to be rocky, and it is likely a gas giant similar to Neptune. The two stars are a sun-like star and a red dwarf, and they orbit each other every 7.5 days. The planet orbits both stars from a distance taking 303 days to complete one orbit. You approach the planet, and the view from orbit shows a world wrapped in clouds. The temperature in the habitable zone is moderate compared to the extremes you have visited. And if the planet has moons, those moons might have conditions suitable for liquid water. The planet itself is gaseous, but moons orbiting a gas giant in a habitable zone represent one possible pathway to habitable environments in binary systems. The two stars are visible from the planet, one much brighter than the other, and they orbit each other so quickly that their relative positions change noticeably over the course of days. The Kepler-47 system contains at least 3 planets, all of them orbiting the binary stars in a compact configuration. The inner planets orbit closer to the stars, and the outer planet, Kepler-47c, orbits farther out where conditions are cooler. The system is stable, and the planets have likely been in their current orbits for millions or billions of years. The discovery of multiple planets in a circumbinary system suggests that planet formation around binary stars is not significantly different from formation around single stars, and it raises the possibility that many binary systems host planets. You set course for a system with not 2, but 4 stars. PH1, also known as Kepler 64b, orbits 2 stars, and those 2 stars are themselves orbited by another pair of stars at a much greater distance. The planet sees 4 suns in its sky, though 2 of them are so far away that they appear as bright stars rather than disks. The 2 close stars are similar in size to the Sun, and they orbit each other every 20 days. The planet orbits both of them every 138 days, and the orbital distance places it in a region that is too hot for liquid water. You descend toward the planet, and the 2 primary stars dominate the sky. The planet is similar in size to Neptune, and it is likely composed mostly of gas with no solid surface. The 2 distant stars are visible during the night, brighter than any other stars in the sky, but far enough away that they provide little heat or light. The 4-star configuration is rare, and the gravitational stability of such a system is remarkable. The planet's orbit must avoid regions where the gravitational pull from the distant binary pair would destabilize it. And the fact that the planet exists in a stable orbit suggests that such systems can remain dynamically stable over long periods. The discovery of PH1 was made by citizen scientists analyzing data from the Kepler mission. The planet transits the 2 close stars, causing tiny dips in brightness that repeat every 138 days, and the pattern was spotted by volunteers who were examining light curves. The discovery highlights the complexity of star systems and the surprising variety of configurations that can support planets. The 4 stars orbit in a hierarchical arrangement, with the 2 close pairs widely separated from each other, and the planet orbits within the inner binary system, stable and secure, despite the presence of 4 stellar masses in the same system. You leave the 4-star system and travel to Kepler 453b, another circumbinary planet, this one located in the habitable zone. The planet orbits 2 red dwarf stars, and the combined light from both stars is much dimmer than the Sun. The planet is about 6 times Earth's radius, making it similar in size to Saturn, and it orbits every 240 days. The habitable zone around red dwarf stars is closer to the stars than around Sun-like stars, and the planet orbits at a distance where temperatures might allow liquid water if it were a rocky world. Unfortunately, the planet is too large to be rocky, and it is almost certainly a gas giant. You approach the planet, and the 2 red dwarf stars are visible, both of them glowing with a deep red color. The stars orbit each other every 27 days, and from the planet's distance, they appear as a close pair, moving together across the sky. The planet's orbit is slightly elliptical, and the distance from the stars varies over the course of the orbit, causing small changes in the amount of light and heat the planet receives. The combined light from the 2 stars is dim, and the habitable zone is narrow, but the planet occupies a position within it. And if it has large moons, those moons might be in a temperate region. The planet was discovered through the transit method, but the transits are not regular. The stars orbit each other, and the planet orbits both stars, and the alignment needed for a transit to occur happens only at certain times. The transits were observed, then stopped, and then resumed years later as the orbital configuration brought the planet back into alignment with Earth's line of sight. This irregular transit pattern is common in circumbinary systems, and it makes detecting such planets more difficult. You move to NN Serpentis, a binary system consisting of two white dwarfs, the remnants of stars that have exhausted their nuclear fuel and collapsed into dense cores. The system contains at least two planets, both of them orbiting the binary pair at distances greater than the orbit of Mars around the Sun. The planets survived the red giant phases of both stars, an achievement that required either extreme luck or significant orbital migration. The white dwarfs orbit each other every 3 hours, and they eclipse each other regularly, creating a predictable pattern of brightness changes. You approach the inner planet, and the two white dwarfs are visible as small, intensely bright points of light. The stars are much smaller than the Sun, only about the size of Earth, but they are extremely hot and dense. The light from the white dwarfs is harsh and blue-white, and the planets receive little warmth because the stars, while hot, are small and emit less total energy than main sequence stars. The planets are likely frozen, with surface temperatures far below anything that would support liquid water, and the environment is bathed in ultraviolet radiation from the white dwarfs. The planets were detected through timing variations in the eclipses. The gravitational pull of the planets affects the orbits of the white dwarfs slightly, and this causes tiny changes in the timing of the eclipses. By measuring these changes over many years, astronomers were able to infer the presence of the planets and calculate their masses and orbital periods. The discovery shows that planets can survive the death of their stars, and it raises questions about what happens to planetary systems as stars evolve off the main sequence and become red giants and then white dwarfs. You leave the white dwarf system and travel to a disputed planet in the Alpha Centauri system. Alpha Centauri is a triple star system, and it is the closest star system to the Sun, located only 4.37 light-years away. The system consists of two Sun-like stars, Alpha Centauri A and B, that orbit each other every 80 years, and a distant red dwarf, Proxima Centauri, that orbits the pair from a much greater distance. A planet was announced around Alpha Centauri B in 2012, but subsequent analysis cast doubt on the discovery, and the planet's existence remains uncertain. If the planet exists, it would orbit Alpha Centauri B every 3.2 days, very close to the star and far too hot for liquid water. The planet would see Alpha Centauri A in the sky as a very bright star, much brighter than any star visible from Earth, and the two stars would move relative to each other over the course of their 80-year orbit. The detection was based on radial velocity measurements, tiny wobbles in the star's motion caused by the gravitational pull of the planet, but the signal was close to the limit of what the instruments could measure, and other explanations for the data have been proposed. The Alpha Centauri system is a prime target for future exoplanet searches because of its proximity to Earth. If planets exist around either of the Sun-like stars, they would be among the easiest to study in detail, and they might even be targets for future interstellar probes. The system is close enough that light from the stars takes only 4 years to reach us, and radio signals would take the same amount of time, making communication with any future mission feasible within human timescales. As you leave the Alpha Centauri system and move away from the worlds with multiple suns, the complexity of binary and multi-star systems becomes clear. Planets in these systems experience variable illumination, with the suns moving across the sky in patterns that depend on the orbital periods of both the stars and the planet. Some planets see double sunsets, others see 4 suns, and some orbit white dwarf pairs that have outlasted their main sequence lifetimes. The gravitational dynamics are intricate, and the stability of these systems depends on the distances and masses involved. But nature has found ways to create stable planetary orbits, even in environments that seem chaotic. The journey continues, and ahead lie planets with orbits that defy the orderly circular paths we see in our own solar system. Worlds that swing wildly between heat and cold, or move backward relative to their star's rotation. You are approaching a planet whose orbit is so elliptical that it resembles a comet more than a typical planet. HD 0782b has an orbital eccentricity of 0.96, which means the orbit is nearly a straight line, swinging the planet from a distant cold aphelion to a scorching close perihelion. The planet is about twice the mass of Jupiter, and it orbits a sun-like star located 117 light-years from Earth. The orbital period is 597 days, and during each orbit, the planet experiences temperature swings that range from -140 degrees Celsius at the farthest point to over 2,200 degrees Celsius at the closest approach. You follow the planet through its orbit, starting at aphelion, where the star is a distant point of light. At this distance, the planet receives very little energy, and the atmosphere is cold. If the planet has clouds, they would be composed of materials that condense at low temperatures, possibly water ice or ammonia. The surface, if there is a solid surface beneath the thick atmosphere, would be frozen, and any heat from the interior would be insufficient to warm the outer layers significantly. The planet drifts slowly through this cold region, spending most of its orbital period far from the star. As the orbit carries the planet inward, the star grows brighter and the temperature begins to rise. The planet accelerates as it falls toward the star, moving faster and faster until it reaches perihelion, the closest point in its orbit. At perihelion, the planet passes within a distance closer than Mercury orbits the Sun, and the temperature spikes dramatically. The atmosphere heats up by more than 1,000 degrees in a matter of weeks, and the sudden energy input creates shockwaves and possibly supersonic winds as the air tries to redistribute the heat. The star dominates the sky, huge and brilliant, and the planet is blasted with radiation. The heating is so rapid that the atmosphere cannot reach equilibrium. The outer layers absorb energy and begin to expand, but before the heat can penetrate deeply, the planet swings past perihelion and begins moving away again. The temperature drops as the planet recedes, and the atmosphere cools and contracts, releasing the heat back into space as infrared radiation. The cycle repeats with every orbit, and the planet never settles into a stable thermal state. Weather patterns on such a world would be extreme, driven by the rapid changes in energy input and the attempts by the atmosphere to respond to conditions that shift faster than equilibrium can be reached. You leave HD 20782b and travel to a planet that orbits its star in the opposite direction from the star's rotation. WASP-17b is a retrograde planet, meaning its orbital motion is backward relative to the spin of the star. The planet is a bloated gas giant, and you visited it earlier for its extreme low density, but now you focus on the unusual orbit. Retrograde orbits are rare, and they suggest a violent history involving gravitational interactions with other planets or passing stars. The planet may have formed in a normal prograde orbit and then been scattered onto a retrograde path through encounters with other massive objects in the system. You enter orbit around WASP-17b, and the star rotates beneath you in one direction, while the planet moves in the opposite direction. The retrograde motion creates a situation where the relative velocity between the planet and the stellar wind is higher than for a prograde orbit, and this may contribute to atmospheric loss. The planet is already losing mass due to its low density and the intense stellar heating, and the retrograde orbit may accelerate this process. The gravitational interactions that caused the retrograde motion likely occurred early in the system's history, when other planets were present and the orbits were still unstable. The planet orbits every 3.7 days, close to the star and moving swiftly through space. The retrograde motion means that from the surface of the star, the planet would appear to move across the sky in the opposite direction from the star's rotation, an unusual configuration that astronomers can detect through precise measurements of the star's motion. The discovery of retrograde planets challenged early models of planetary system formation, which assumed that planets would naturally orbit in the same direction as the star's rotation, because they formed from a disk of material that was itself rotating with the star. You leave WASP-17b and head to HAT P7b, another retrograde world. This planet is about 1.8 times the mass of Jupiter, and it orbits a star hotter than the Sun every 2.2 days. The retrograde orbit suggests a history of gravitational scattering, and the planet may have interacted with other planets that have since been ejected from the system or fallen into the star. The close orbit and high stellar temperature create conditions similar to other hot Jupiters, with the day side reaching temperatures above 2,600 degrees Celsius. You approach the planet, and the retrograde motion is evident from the way the star's rotation and the planet's orbit are misaligned. The planet's atmosphere shows evidence of strong winds, and observations have revealed that the hottest point on the planet is offset from the subsolar point, shifted eastward by high-altitude jet streams. The retrograde orbit adds complexity to the atmospheric dynamics, and the interaction between the stellar wind and the planet's motion may create unique features in the upper atmosphere. The clouds on this world may be made of corundum, and the winds transport heat and cloud material in patterns shaped by both the planet's rapid rotation and its backward orbital motion. You move to HR 5183b, a planet with an orbit so eccentric that it has been nicknamed the whiplash planet. The orbital eccentricity is 0.84, and the planet swings from a distance similar to Jupiter's orbit down to a close approach near the habitable zone of the star. The planet is about 3 times the mass of Jupiter, and the extreme orbit suggests it may have scattered other planets out of the system during its formation. The star is slightly more massive than the Sun, and it is located 103 light-years from Earth. You follow the planet through its orbit, and the pattern is similar to HD 20782b, but less extreme. The planet spends most of its time in the outer regions of the system, moving slowly through cold space, where temperatures are far below freezing. As it swings inward, it accelerates and the temperature rises, reaching a peak during the brief close approach before the planet swings back outward again. The orbital period is 74 years, which means the planet completes its whiplash motion only once in a human lifetime, and astronomers have observed only a fraction of one full orbit. The presence of such an eccentric orbit raises questions about the history of the system. Planets do not form in highly elliptical orbits. They start in nearly circular paths within the protoplanetary disk. Something must have perturbed the orbit, either gravitational interactions with other planets or an encounter with a passing star. The whiplash planet may be the sole survivor of a multi-planet system that experienced instability, with the other planets ejected or consumed by the star, while HR 5183b was scattered onto its current extreme orbit. You travel to Exo 3b, a massive planet with an orbit tilted 37 degrees relative to the star's equator. The planet is about 13 times the mass of Jupiter, right at the boundary between planet and brown dwarf, and the tilted orbit suggests it did not form in the protoplanetary disk, but was scattered onto its current path. The planet orbits every 3.2 days, very close to the star, and the orbital eccentricity is moderate, adding to the complexity of the system. The mass of the planet places it in an uncertain category, and whether it should be called a planet or a brown dwarf depends on how it formed. You approach Exo 3b, and the tilt of the orbit is evident from the way the planet's path cuts across the star's equator at a steep angle. The gravitational interactions required to tilt an orbit this much are significant, and the planet may have experienced close encounters with other massive objects early in its history. The planet is large and massive, and the gravity at the cloud tops is strong enough to compress the atmosphere and prevent the kind of inflation seen on lower mass hot Jupiters. The planet's density is higher than Jupiter's, and the interior is likely composed of a significant amount of rock and metal in addition to hydrogen and helium. You leave Exo 3b and travel to Kepler 413b, a planet with an orbit that wobbles. The planet orbits a binary star system, and the gravitational pull from the two stars causes the planet's orbital plane to precess, shifting its orientation over an 11-year cycle. This precession means that the planet's transits, as seen from Earth, are not regular. The planet transits the stars for a period of time, then stops transiting as the orbital plane tilts away from our line of sight, and then resumes transiting years later when the precession brings the orbit back into alignment. You enter the system, and the two stars are visible orbiting each other every 10 days. The planet orbits both stars from a distance, taking 66 days to complete one circuit. The wobble in the orbit is caused by the torque exerted by the binary stars, and the precession is a natural consequence of the gravitational dynamics in a circumbinary system. The planet is about 4 times Earth's radius, and it is likely a gas giant or a large rocky planet with a thick atmosphere. The precession makes the planet difficult to study because the transits are intermittent, but it also provides valuable information about the planet's orbit and the gravitational forces acting on it. You move to GJ 436b, a planet you visited earlier for its exotic hot ice, but now you focus on its orbit and the strange features that surround it. The planet has a small but measurable orbital eccentricity, which is unusual for a planet orbiting so close to its star. Tidal forces should have circularized the orbit over time, but GJ 436b retains a slight ellipse, possibly maintained by gravitational interactions with another planet in the system. The planet is also losing hydrogen from its atmosphere, and this hydrogen forms a trailing cloud that extends behind the planet like a comet tail. You approach the planet, and the hydrogen cloud is visible as a faint glow surrounding the planet and stretching away from the star. The cloud is created by the intense radiation from the red dwarf star, which heats the upper atmosphere and allows hydrogen to escape into space. The escaping hydrogen is ionized by the stellar wind, and it forms a tail that points away from the star, visible through observations in ultraviolet light. The planet is slowly losing mass, and over millions of years, the hydrogen envelope will shrink, though the rocky core beneath will remain intact for billions of years to come. You observe the eccentric orbit more closely, and the small ellipse becomes apparent in the way the planet's distance from the star varies slightly over each orbit. The eccentricity may be maintained by a second planet farther out in the system, one that has not yet been directly detected, but whose gravitational influence prevents the orbit from circularizing completely. The hydrogen tail streaming behind GJ 436b is one of the most dramatic examples of atmospheric escape ever observed, and it demonstrates how even small planets can lose significant amounts of material when subjected to intense stellar radiation over long periods of time. You leave the trailing cloud of GJ 436b and move to Kepler 432b, a massive planet spiraling slowly inward toward its star. The planet is about 6 times the mass of Jupiter, and it orbits a red giant star every 52 days. The orbit is eccentric, with an eccentricity of about 0.5, and tidal interactions between the planet and the star are slowly reducing the orbital distance. Within the next 200 million years, the planet will spiral into the star and be destroyed, consumed by the expanding outer layers of the red giant. You approach Kepler 432b, and the red giant star looms large in the sky, swollen and luminous, its outer layers cool and orange-red. The planet orbits close enough that the star's gravity is pulling on it, creating tidal bulges in both the planet's atmosphere and the star's outer envelope. These tidal interactions dissipate energy as heat, and the energy loss causes the orbit to decay slowly but steadily. The planet's fate is sealed, and every orbit brings it slightly closer to the star, accelerating the process as the tidal forces increase with decreasing distance. The star itself is in a late stage of evolution, having exhausted the hydrogen in its core and expanded into a red giant. The planet may have originally formed much farther out in the system, in a stable orbit that would have lasted billions of years, but the star's expansion and the redistribution of mass during the red giant phase altered the gravitational landscape of the system. The planet migrated inward, either through tidal interactions or through scattering by other planets, and now it is doomed to fall into the star. This scenario may be common in planetary systems around evolved stars, and it offers a preview of the distant future of our own solar system, when the Sun becomes a red giant and potentially consumes the inner planets. You move away from Kepler 432b, leaving behind the doomed world and its aging star, and you reflect on the variety of orbital configurations you have encountered in this part of the journey. Some planets swing through extreme ellipses, experiencing wild temperature variations with every orbit. Others move backward relative to their stars, their retrograde orbits the result of violent gravitational interactions early in their history. Some orbits are tilted, some wobble, and some are slowly decaying, bringing the planet ever closer to destruction. These orbital oddities reveal the dynamic and sometimes chaotic nature of planetary systems, where gravitational interactions, close encounters, and the evolution of the central star can reshape orbits and send planets onto paths far different from the ones they started on. The orbits you have seen are not the orderly, nearly circular paths that characterize the planets in our solar system. They are extreme, eccentric, tilted, and unstable, shaped by forces that acted long ago or that continue to act today. Each unusual orbit tells a story about the history of the system, about planets that once existed but are now gone, about close encounters that sent worlds spinning onto new trajectories, and about the slow but relentless forces of tidal interactions that are still reshaping these systems today. The universe creates planets in a wide variety of orbits, and the strangeness of these paths is a testament to the complexity and diversity of planetary system formation and evolution. You are approaching a planet that absorbs almost all the light that falls on it, reflecting less than 1% back into space. TRES 2b is the darkest known planet, blacker than coal or asphalt, and it orbits a sun-like star 750 light-years from Earth. The planet is about the size of Jupiter, and it completes one orbit every 2.5 days, locked in a close embrace with its star. The temperature on the day side reaches about 1,800 degrees Celsius. Yet, despite this heat, the planet remains remarkably dark. You approach TRES 2b from a distance, and the planet is difficult to see against the background of space. It appears as a black sphere, outlined only by the faint glow of light from the star that manages to reach your position. The planet does not shine like other gas giants, which typically reflect a significant portion of the light that strikes them. Instead, TRES 2b absorbs the light, and the energy is converted into heat deep within the atmosphere. The darkness may be caused by chemicals in the atmosphere that are particularly effective at absorbing light, possibly vaporized sodium, potassium, or titanium oxide, though the exact composition remains uncertain. You enter orbit around the planet, and the surface below is barely visible, a faint dark disk against the starlight. The atmosphere is thick and hot, and the chemicals that create the darkness are mixed throughout the upper layers, preventing light from penetrating deeply or reflecting back. The planet is so dark that it would be nearly invisible if it were not for the slight amount of thermal radiation it emits, glowing faintly in the infrared from the heat of its day side. The discovery of TRES 2b challenged expectations about planetary albedo, and it demonstrated that gas giants can have a wide range of reflectivity depending on their atmospheric composition and temperature. You leave the dark world behind and travel to a planet that reflects light much more effectively. Kepler 7b is a gas giant with high-altitude clouds that create bright patches visible from space. And it was one of the first exoplanets to have its cloud patterns mapped. The planet is about 1.5 times the radius of Jupiter, and it orbits a sun-like star every 4.9 days. The clouds are likely composed of silicate particles, similar to the glass rain on HD 189733b, but on Kepler 7b, the clouds are located high in the atmosphere, and they reflect a significant amount of starlight. You approach Kepler 7b, and the planet appears brighter than most hot Jupiters, with patches of clouds visible as lighter regions on the day side. The clouds are not evenly distributed. They are concentrated to the west of the point where the star is directly overhead, shifted by atmospheric winds that blow from the day side toward the night side. The wind patterns create a circulation that carries cloud material away from the hottest region, and the clouds condense at slightly cooler temperatures, forming the bright reflective patches that astronomers have mapped using variations in the planet's light curve. You descend into the atmosphere, and the clouds surround you, particles of silicate floating in the upper layers, scattering light and creating haze. The temperature here is lower than on the darkest planets, allowing the clouds to remain stable rather than evaporating completely. The mapping of Kepler 7b's clouds was achieved by measuring how the brightness of the planet changed as it rotated, with brighter regions producing more reflected light and darker regions absorbing more. This technique revealed the distribution of clouds and provided insight into the atmospheric dynamics of hot Jupiters. You leave Kepler 7b and move to LTT 9779b, a planet that should not exist. The planet is about the size of Neptune, and it orbits its star every 19 hours, placing it well within the region known as the Neptune Desert, a zone close to stars where planets of Neptune's size are extremely rare. The planet is so close to its star that the temperature reaches over 1,700 degrees Celsius, and the intense radiation should have stripped away the planet's atmosphere long ago, leaving behind only a bare rocky core. You approach LTT 9779b, and the planet is not only present, but it is also highly reflective, with an albedo much higher than expected for such a hot world. The atmosphere is still intact, thick and extended, and it reflects a significant portion of the starlight that hits it. The planet's survival in the Neptune Desert is a mystery, and it suggests that either the planet formed very recently and has not yet lost its atmosphere, or it has some mechanism for retaining or replenishing the atmospheric gases despite the intense stellar heating. You enter orbit, and the planet below is bright, its atmosphere glowing with reflected light and thermal emission. The discovery of LTT 9779b challenged models of planetary evolution that predicted Neptune-sized planets would lose their atmospheres when orbiting this close to their stars. The planet may have migrated inward recently from a more distant orbit, or it may possess a core massive enough to hold onto the atmosphere through sheer gravitational force. The mystery remains under investigation, and future observations may reveal the processes that allow this planet to survive in such an extreme environment. You move to WASP 79b, a hot Jupiter with a clear atmosphere that allows astronomers to see deep into the planet's structure. The planet orbits its star every 3.7 days, and the atmosphere is notably free of clouds and haze, which makes it easier to detect the chemical signatures of gases present in the atmosphere. Observations have revealed a strong signature of sodium, which appears as a yellow color in spectroscopic data, and the clarity of the atmosphere allows this signature to be seen more clearly than on planets with thick cloud decks. You approach WASP 79b, and the planet appears as a pale orb, with the atmosphere transparent enough that light from the star can penetrate deeply before being absorbed or scattered. The lack of clouds may be due to the planet's temperature and atmospheric chemistry, which prevent the formation of high-altitude condensates that create haze on other worlds. The clear skies make WASP 79b an excellent target for atmospheric studies, and detailed spectroscopy has revealed the presence of sodium, water vapor, and possibly other molecules in the atmosphere. You descend toward the atmosphere, and the transparency becomes evident as you pass through the upper layers. There is no thick haze to obscure your view, no dense cloud deck to block the light, just the clear gas of the atmosphere extending downward toward the interior. The temperature rises as you descend, and eventually the pressure becomes too great to continue. But the clarity of the upper atmosphere has provided valuable data about the composition and structure of hot Jupiter atmospheres. You leave WASP 79b and travel to WASP 31b, another planet with a cloudless atmosphere. This planet orbits its star every 3.4 days, and observations have shown that the atmosphere lacks the clouds and haze that are common on many hot Jupiters. The absence of clouds allows clear detection of sodium in the atmosphere, and the planet has become a benchmark for studying atmospheric chemistry without the complications introduced by cloud cover. You approach WASP 31b, and the planet's atmosphere is open and transparent, similar to WASP 79d. The cloudless sky reveals the chemical composition more directly, and the strong sodium signature confirms that the atmosphere is free of the high-altitude hazes that obscure this feature on other planets. The reasons for the lack of clouds are not fully understood, but they may be related to the planet's temperature, atmospheric circulation, or chemical composition, all of which influence whether condensates can form and persist in the upper atmosphere. You move to HAT P2 6b, a Neptune-sized planet with a primitive atmosphere that has a low metallicity compared to Neptune in our solar system. The planet is smaller than Neptune, and it orbits a star cooler than the Sun every 4.2 days. The atmosphere is mostly hydrogen and helium, with relatively few heavier elements, and this composition is more similar to the primordial gas of the early solar system than to the enriched atmospheres of Neptune and Uranus. You approach HAT P26b, and the planet is less reflective than the bright worlds you visited earlier, but it is not as dark as TRES 2b. The atmosphere is thick and extended, and the low metallicity suggests that the planet either formed early in the disk's evolution before heavy elements were fully mixed in, or it accreted its atmosphere from gas that was unusually pristine. The discovery of HAT P26b's primitive atmosphere was surprising because Neptune and Uranus in our solar system have much higher metallicities. And the difference suggests that planetary atmospheres can vary widely depending on where and when they formed. You descend into the atmosphere, and the gas around you is thin in heavier elements, composed primarily of hydrogen and helium, with only trace amounts of water vapor, methane, or other compounds. The simplicity of the composition makes the atmosphere easier to model, and it provides a glimpse into what planetary atmospheres might have looked like in the early stages of planetary system formation, before heavier elements were fully incorporated into the gas. You leave HAT P26b and move to Kepler-10b, the first confirmed rocky exoplanet ever discovered. The planet is about 1.4 times the radius of Earth, and it orbits its star every 20 hours, completing more than 400 orbits in a single Earth year. The planet is scorched by the proximity to its star, with a dayside temperature exceeding 2,500 degrees Celsius, hot enough to melt rock and vaporize metals. You approach Kepler-10b, and the planet glows faintly with its own heat, the surface radiating thermal energy into space. The rocky surface is likely molten on the day side, with lava flows and possibly lakes of molten rock covering the hemisphere that faces the star. The night side is cooler, but the temperature is still far too high for solid rock to remain stable on the surface. The planet's brightness is dominated by thermal emission rather than reflected light, and the surface would glow red or orange from the intense heat. You enter orbit above the day side, and the molten surface stretches out below, a landscape of glowing rock and extreme temperatures. Kepler-10b was a landmark discovery because it confirmed that rocky planets exist around other stars, and it opened the door to the search for Earth-like worlds in the habitable zones of their stars. The planet itself is far from habitable, but its existence proved that small, rocky planets are common in the galaxy, and it provided the first direct evidence of a terrestrial exoplanet. The contrast between the darkest planet you visited, TRES 2b, and the brighter, more reflective worlds like Kepler-7b and LTT 9779b illustrates the wide range of albedos and atmospheric properties that exoplanets can possess. Some planets absorb nearly all the light that hits them, remaining dark and mysterious, while others reflect light efficiently, their clouds and clear skies making them bright targets for observation. the cloudless atmospheres of WASP 79b and WASP 31b allow astronomers to probe the chemical composition directly, while the primitive atmosphere of HATP 26b offers a window into the early conditions of planetary formation. The rocky surface of Kepler-10b glows with its own heat, a world so close to its star that the surface is molten and the planet shines from thermal emission rather than reflected starlight. You are approaching the oldest planet ever discovered, a world that has existed for 12.7 billion years, longer than most stars currently burning in the galaxy. PSRB 162026b, sometimes called Methuselah, orbits a binary system consisting of a pulsar and a white dwarf, and the planet is located in the globular cluster Messier 4, about 12,000 light-years from Earth. The planet is about 2.5 times the mass of Jupiter, and it orbits both stellar remnants from a vast distance, taking roughly 100 years to complete a single orbit. You approach the system, and the pulsar is visible as a rapidly spinning neutron star, its beam of radiation sweeping past you with precise regularity. The white dwarf orbits the pulsar every 6 months, and the planet orbits both stars from a distance of roughly twice the distance between the Sun and Uranus. The planet formed when the universe was only about 1 billion years old, and it has survived through the entire history of stellar evolution in the cluster, witnessing the birth and death of countless stars over billions of years. You enter orbit around Methuselah, and the planet below is cold and dark, far from both the pulsar and the white dwarf. The planet receives almost no light or heat from its stellar companions, and the surface temperature is likely far below freezing, possibly approaching the temperature of interstellar space. The planet formed in an era when the universe contained very few heavy elements, and its composition may be different from planets that formed later, when the interstellar medium had been enriched by supernova explosions. Despite the metal-poor environment, the planet exists, demonstrating that planetary formation can occur even in the early universe. You leave Methuselah and travel to the Kepler 444 system, a star that is 11.2 billion years old and hosts 5 small planets, all smaller than Earth. The star formed when the Milky Way was still young, and the planets are among the oldest rocky worlds ever discovered. The planets orbit very close to the star, with the outermost planet completing its orbit in less than 10 days, and all 5 planets are too hot to support life. But their existence shows that small rocky planets formed early in the galaxy's history. You approach the Kepler 444 system, and the 5 planets are visible in their tight orbits, each one smaller than Earth and likely composed of rock and metal. The star is cooler and smaller than the Sun, a K-type star that has been burning steadily for over 11 billion years. The planets formed from a protoplanetary disk that was relatively poor in heavy elements compared to the disks around younger stars. Yet, the planets exist, their rocky cores assembled from the limited supply of metals available in the early galaxy. You observe the planets from a distance, and the ancient system stretches out before you, a family of worlds older than Earth by more than 7 billion years. The discovery of the Kepler 444 planets was significant because it demonstrated that terrestrial planets formed throughout the history of the galaxy, and it raised the possibility that habitable planets could have existed for billions of years before Earth even formed, potentially hosting life that arose and evolved long before our own solar system came into being. You move to the Captain star system, another ancient star located only 13 light-years from Earth. Captain's star is a red dwarf about 11 billion years old, and it hosts at least one planet, Captain B, which is about 5 times the mass of Earth and orbits the star every 48 days. The star is a member of the galactic halo, a population of old stars that orbit the Milky Way in paths that take them above and below the disk, and its metal-poor composition indicates it formed early in the galaxy's history. You approach Captain B, and the planet is larger than Earth, likely a super-Earth, with a rocky core and possibly a thick atmosphere. The star is cool and red, and the planet orbits close enough to receive some warmth, though the red dwarf's luminosity is much lower than the Sun's. The planet's age and composition make it an intriguing target for study, and it represents the kind of world that could have existed for billions of years, potentially long enough for life to arise and evolve if the conditions were suitable. You leave the ancient worlds and travel forward in time to the youngest planets known, worlds that are still forming or have only recently finished accreting their mass. You arrive at the PDS-70 system, a young star about 5 to 6 million years old, surrounded by a circumstellar disk from which 2 planets are currently forming. PDS-70b and PDS-70c are embedded in the disk, and they are clearing gaps in the material around them as they sweep up gas and dust with their gravity. You approach PDS-70b, the inner planet, and the protoplanetary disk surrounds you, a vast expanse of gas and dust glowing faintly in the infrared from the heat of the forming planets. The planet itself is several times the mass of Jupiter, and it is surrounded by a circumplanetary disk, a smaller disk of material that is spiraling into the planet and adding to its mass. The planet glows with the heat of accretion, and the disk material rains down onto the planet's atmosphere, releasing energy as it falls. You observe PDS-70c farther out in the system, another planet still forming, also embedded in the disk and accreting material. The 2 planets are sculpting the disk, their gravity creating gaps and spiral arms in the gas and dust, and the entire system is a snapshot of planetary formation in progress. The direct imaging of these forming planets was a major achievement in astronomy, and it confirmed many of the predictions made by models of how planets grow from disks of material around young stars. You move to V830 Tauri b, one of the youngest hot Jupiters known, only about 2 million years old. The planet orbits a T Tauri star, a young star that is still contracting and has not yet settled onto the main sequence. The planet is about 3/4 the mass of Jupiter, and it orbits the star every 4.9 days. Very close in for such a young system. The discovery of V830 Tauri b was surprising because hot Jupiters were thought to migrate inward over tens of millions of years. Yet this planet has already reached a close orbit while the star is still surrounded by its protoplanetary disk. You approach V830 Tauri b, and the young star is active and variable, with strong magnetic fields and frequent flares. The planet orbits close enough that it is bathed in intense radiation, and the protoplanetary disk is still present farther out in the system, a sign that planet formation is ongoing. The rapid migration of this hot Jupiter suggests that some planets move inward much faster than previously thought, possibly through interactions with the disk material or with other planets in the system. You leave V830 Tauri b and travel to K2-33b, another young planet, between 5 and 10 million years old. The planet is about 5 times the radius of Earth, and it orbits its star every 5 days. The star is a young pre-main sequence star, and the planet is one of the youngest, fully formed planets ever detected. The planet has not yet contracted to its final size, and it may still be losing heat from its formation, glowing faintly in the infrared as it gradually cools and settles into its final configuration. You approach K2-33b, and the planet is larger than it will be in the future, its atmosphere extended by the heat of formation and the low density of the young gas envelope. The discovery of K2-33b demonstrated that planets can reach close orbits very early in their history, and it provided evidence that migration happens quickly, possibly within the first few million years of a planetary system's existence. You move to 2M0437b, one of the youngest directly imaged planets, only a few million years old. The planet is several times the mass of Jupiter, and it orbits a young star at a distance of roughly 100 astronomical units. The planet is still warm from its formation, glowing with infrared radiation as it slowly cools over millions of years. The direct imaging of 2M0437b was possible because the planet is young and bright, and it has not yet faded to the point where it would be lost in the glare of its star. You approach 2M0437b, and the planet appears as a faint reddish point of light, its thermal glow the remnant of the gravitational energy released during its formation. The planet orbits far from its star, and it may have formed at that distance, or migrated outward after forming closer in. The youth of the planet makes it an ideal target for studying the early stages of planetary evolution, and observations of its atmosphere may reveal details about the composition and structure of newborn gas giants. You leave the young planets and reflect on the span of time represented by the worlds you have visited in this part of the journey. Methuselah has existed for 12.7 billion years, older than the Sun, older than Earth, a planet that formed when the universe was still in its infancy. The Kepler 444 planets and Captain B are nearly as old, witnesses to the early history of the galaxy, and their existence demonstrates that rocky planets have been forming for most of cosmic history. On the other end of the spectrum, PDS 70b and C are still forming, embedded in their protoplanetary disk, adding mass with every orbit. V830 Tauri b, K2, 33b, and 2M0437b are all only a few million years old, newborns compared to the ancient worlds. Yet they are already following the paths that will define them for billions of years to come. The age of a planet shapes its characteristics in subtle ways. Older planets have had time to cool, lose atmospheric mass, and settle into stable configurations. Younger planets are still warm from formation, their atmospheres extended, and their orbits possibly still changing as they interact with the remnants of the protoplanetary disk. The universe has been forming planets for over 12 billion years, and the variety of ages represented among the known exoplanets shows that planet formation is not a rare or recent phenomenon, but a continuous process that has been occurring throughout the history of the galaxy. You are approaching a planet that survived one of the most violent events a planetary system can experience. Kepler 70b orbits the core of a red giant star, a hot subdwarf that is all that remains after the star exhausted its hydrogen and helium and shed its outer layers. The planet is likely the remnant core of a gas giant, stripped of its atmosphere when the star expanded into a red giant and engulfed the planet's orbit. The planet now circles the stellar core every 5.76 hours, closer to its star than any other known planet, and the surface temperature exceeds 7,000 degrees Celsius. You approach Kepler 70b, and the subdwarf star shines intensely, small but incredibly hot, its surface temperature around 27,000 degrees Celsius. The planet is tiny by comparison, likely composed of heavy elements like iron and rock, the remnants of the gas giant's core that survived the engulfment. The surface of the planet would be molten or vaporized, and the extreme heat means that the planet is glowing brightly with thermal emission. The discovery of Kepler 70b demonstrated that planets can survive the red giant phase, though they are often transformed beyond recognition in the process. You observe Kepler 70c farther out, another remnant planet orbiting the same star every 8.23 hours. Both planets orbit in the zone where they would have been inside the red giant's envelope, and they likely lost their atmospheres and possibly significant portions of their mass during that phase. The survival of these planets suggests that cores can endure even when the outer layers are stripped away, and it provides a glimpse of what might happen to planets in our solar system when the Sun becomes a red giant in about 5 billion years. You leave the Kepler 70 system and travel to WD 1856 plus 534b, a Jupiter-sized planet orbiting a white dwarf every 34 hours. The planet is much larger than the white dwarf, and it orbits very close, passing in front of the stellar remnant and creating transits that are visible from Earth. The white dwarf is the leftover core of a sun-like star that exhausted its fuel and shed its outer layers, and the planet somehow survived the star's evolution and migrated inward to its current close orbit. You approach WD 1856 plus 534b, and the white dwarf is visible as a small, dense object, about the size of Earth, but containing about half the mass of the Sun. The planet looms large above the white dwarf, and the contrast in size is striking. How the planet survived the red giant phase is a mystery, and it may have been farther out in the system when the star expanded and then migrated inward after the star shed its envelope. Alternatively, the planet may have formed after the star became a white dwarf, assembled from the debris left behind by the shedding process, though this scenario is considered less likely. You enter orbit around the planet, and the white dwarf provides little light, its luminosity much lower than a main sequence star. The planet is cold and dark, far from the warmth of a living star, and the system is a quiet, fading remnant of what was once a vibrant planetary system. The discovery of WD 1856 plus 534b was significant because it showed that planets can survive stellar death, and it raised the possibility that white dwarf systems may host many planets that went undetected until transit surveys became sensitive enough to find them. You move to 8 Ursae Minoris b, a planet that is in the process of being engulfed by its red giant star. The planet is about 1.5 times the mass of Jupiter, and it orbits the star every 93 days. The star has expanded into a red giant, and the planet's orbit lies within the zone that will eventually be inside the star's outer envelope. The planet is slowly spiraling inward due to tidal interactions, and it will be consumed by the star within the next few 100 million years. You approach 8 Ursae Minoris b, and the red giant star fills much of the sky, its outer layers cool and diffuse, glowing orange-red. The planet orbits within the star's extended atmosphere, and the tidal forces are drawing the planet closer with each orbit. The planet's fate is sealed, and it provides a preview of what will happen to planets like Earth when the Sun expands into a red giant, potentially engulfing Mercury, Venus, and possibly Earth itself. You leave 8 Ursae Minoris b and travel to PS R1257 plus 12, a pulsar system located about 2,300 light-years from Earth. This system is historically significant because it was the site of the first confirmed exoplanet discovery in 1992, years before the first exoplanet around a sun-like star was found. The pulsar hosts at least 3 planets, and they orbit the neutron star at distances comparable to the inner planets of our solar system. You approach the pulsar, and the neutron star is small, only about 20 kilometers in diameter, but incredibly dense, with a mass greater than the Sun's. The pulsar rotates rapidly, and its magnetic field generates beams of radiation that sweep across space like a lighthouse. You observe the timing of the pulsar's pulses, and the tiny variations in the pulse arrival times reveal the presence of the planets, their gravity tugging on the pulsar and causing it to wobble slightly in space. You move closer to PS R1257 plus 12b, the innermost planet, which is only about twice the mass of Earth's moon and orbits every 25 days. The planet is bathed in intense radiation from the pulsar, and the surface is likely sterilized by the high-energy particles and electromagnetic waves that sweep over it with each rotation of the neutron star. The planet may be a remnant of a larger body that was destroyed during the supernova that created the pulsar, or it may have formed from the debris left behind after the explosion. You observe PS R1257 plus 12c and D, the 2 larger planets, each about 4 times the mass of Earth. They orbit farther out, at distances of about 0.4 and 0.5 astronomical units, and they are locked in a resonance with their orbital periods in a ratio of about 3:2. The planets are rocky, and they orbit in a quiet, stable configuration despite the violent history of the system. The discovery of these planets was groundbreaking because it demonstrated that planets can form or survive in environments far more extreme than anyone had imagined. You leave the pulsar system and move to WASP-18b, a massive planet that is spiraling toward its star and will fall into it in less than 1 million years. The planet is about 10 times the mass of Jupiter, and it orbits its star every 23 hours, one of the shortest orbital periods known. The tidal interactions between the planet and the star are strong, and they are causing the orbit to decay rapidly, drawing the planet closer with each orbit. You approach WASP 18b, and the star is large and luminous, a main sequence star, hotter than the Sun. The planet orbits so close that the tidal forces are distorting both the planet's atmosphere and the star's magnetic field, creating bulges and possibly generating heat through friction as the two bodies pull on each other. The planet's mass is so large that its gravity is significant even compared to the star, and the mutual tidal interactions are accelerating the orbital decay. You enter orbit above the planet, and the star dominates the sky, close and overwhelming. The planet's atmosphere is heated to extreme temperatures, and the gravity at the cloud tops is strong, preventing the atmosphere from inflating despite the intense heating. The planet will not survive much longer on cosmic timescales, and within 1 million years, it will spiral into the star and be destroyed, adding its mass to the star and briefly increasing the star's luminosity as the material falls inward and releases energy. You move to WASP 189b, a planet that orbits the hottest star known to host a planet. The star is an A-type star with a surface temperature of about 8,000 degrees Celsius, and the planet orbits every 2.7 days at a distance closer than Mercury orbits the Sun. The planet's dayside temperature exceeds 3,200 degrees Celsius, and the intense stellar radiation is likely stripping away the planet's atmosphere at a significant rate. You approach WASP 189b, and the star is brilliant and blue-white, far hotter and more luminous than the Sun. The planet is a hot Jupiter, and it is being blasted with ultraviolet and X-ray radiation from the star, heating the upper atmosphere to extreme temperatures and allowing gas to escape into space. The planet's orbit is slightly elliptical, and the tidal interactions with the star may be preventing the orbit from circularizing, maintaining the slight eccentricity over time. You observe the planet from a distance, and the extreme environment is evident in the glow of the dayside and the likely escape of atmospheric material into space. The planet's survival in such a harsh environment is a testament to the range of conditions under which planets can exist, and it provides an extreme example of the effects of stellar radiation on planetary atmospheres. You leave WASP 189b and reflect on the planets you have encountered in this part of the journey, all of which exist in extreme environments shaped by the life cycles of their stars. Kepler 70b and C survived being engulfed by a red giant and now orbit the exposed core. WD 1856 plus 534b survived its star's death and now circles a white dwarf. 8 Ursae Minoris b is in the process of being consumed by its expanding star. The pulsar planets orbit a neutron star, the remnant of a supernova, and they are bathed in radiation that would destroy any life. WASP 18b is spiraling toward its doom, and WASP 189b orbits in the scorching radiation field of an A-type star. Each of these worlds exists in conditions that test the limits of planetary survival, and each one reveals something about how planets interact with their stars at different stages of stellar evolution. You are approaching a planet that defies current models of planetary structure. TOI 849b is about the size of Neptune but has the mass of roughly 40 Earths, making it far denser than any gas giant should be. The planet orbits its star every 18 hours, and the density suggests it is composed almost entirely of rock and metal, with little or no gaseous envelope. The planet appears to be an exposed planetary core, stripped of its atmosphere by some process that removed the hydrogen and helium that would normally surround such a massive world. You approach TOI 849b, and the planet is visible as a dense, rocky sphere, its surface likely molten from the intense heat generated by the proximity to the star. The planet should have retained a thick atmosphere given its mass and gravity, but the atmosphere is gone, leaving only the core. The most likely explanation is that the planet was once a gas giant, similar to Jupiter or Saturn, and the atmosphere was stripped away either by photoevaporation from the intense stellar radiation or by a giant impact with another planet that ejected the gaseous envelope into space. You enter orbit, and the surface below is bare rock and metal, heated to extreme temperatures by the star's energy. The discovery of TOI 849b was significant because it provides direct evidence that planetary cores can be exposed, and it offers a rare glimpse of the interior structure of what was likely once a much larger planet. The planet's existence challenges formation models that predict gas giants should retain their atmospheres at such close distances. And it suggests that planetary evolution can involve dramatic loss of mass under certain conditions. You leave TOI 849b and travel to LTT 9779b, a planet you visited earlier for its unexpected survival in the Neptune desert. The planet is about the size of Neptune and orbits its star every 19 hours. Yet, it has retained a thick atmosphere despite the intense radiation that should have stripped it away. The planet's survival is unexplained, and it represents one of the ongoing mysteries in exoplanet science. The atmosphere is highly reflective, and observations suggest it contains metals and possibly clouds, but the mechanism that allows the atmosphere to persist remains uncertain. You approach LTT 9779b, again, focusing now on the mystery of its existence rather than its brightness. The planet may have migrated inward recently, arriving at its current orbit too quickly for the atmosphere to be fully removed. Alternatively, the planet's core may be so massive that its gravity can hold on to the atmosphere even under intense heating, or the atmosphere may be replenished by outgassing from the interior, replacing the gas lost to space at a rate that maintains the envelope over time. You move to NGTS 1b, a gas giant that orbits a small M-dwarf star. The planet is about 3/4 the mass of Jupiter, and it orbits every 2.6 days, but the star is only half the mass of the Sun. The planet-to-star mass ratio is unusually high, and current formation models struggle to explain how such a massive planet could form around such a small star. The protoplanetary disk around an M-dwarf would contain less material than the disk around a Sun-like star, and forming a Jupiter-mass planet in that environment requires more efficient accumulation of gas and dust than models typically predict. You approach NGTS 1b, and the small red star is visible, cool and dim compared to the Sun, yet somehow hosting a large gas giant. The planet orbits close, and the star-planet system is unusual in its proportions, with the planet representing a significant fraction of the total system mass. The discovery of NGTS 1b was surprising, and it has prompted revisions to models of planet formation around low-mass stars, suggesting that gas giants may be more common around M-dwarfs than previously thought. You leave NGTS 1b and travel to OGLE 2016 BLG 1928 pounds, a planet discovered by gravitational microlensing that has the highest known planet-to-star mass ratio. The planet is several times the mass of Jupiter, and it orbits what is likely a brown dwarf or a very low-mass star. The mass ratio is so extreme that the planet is almost as massive as its host, and the system blurs the line between a planet-star system and a binary system of similar mass objects. You approach the system, and the host object is faint and difficult to see, likely a brown dwarf that never ignited hydrogen fusion in its core. The planet orbits at a distance of roughly 2 astronomical units, and the gravitational interaction between the two objects is significant, with each one pulling on the other in a mutual orbit around their common center of mass. The formation of such a system is uncertain, and it may have formed more like a binary star system than a traditional planet forming in a protoplanetary disk. You move to Fomalhaut b, a planet whose existence has been questioned. The planet was discovered in 2008 through direct imaging, appearing as a faint point of light moving around the star Fomalhaut. However, subsequent observations showed that the object faded over time, and by 2014 it had nearly disappeared. The leading explanation is that Fomalhaut b was never a planet at all, but a temporary cloud of dust created by the collision of 2 large asteroids or comets. The dust cloud expanded and dispersed over time, and the planet vanished as the particles spread out and became too diffuse to detect. You approach the region where Fomalhaut b was observed, and the dust belt around the star is visible, a ring of debris left over from the formation of the planetary system. The spot where the planet appeared is now empty, with no sign of the object that was once thought to be a gas giant. The story of Fomalhaut b is a reminder that not all detections are confirmed, and that the process of discovering and characterizing exoplanets is complex and sometimes leads to false positives or misinterpretations of the data. You leave Fomalhaut and move to Boyajian's star, also known as KIC 846 2852, a star that has exhibited irregular dimming that defies conventional explanation. The star undergoes sudden, deep dips in brightness that are not periodic and do not match the pattern expected from transiting planets. The dimming events can last for days or weeks, and the amount of light blocked can be as much as 20%, far more than any planet could cause. You approach Boyajian's star, and the star appears normal at first, a main sequence F-type star about 1.4 times the mass of the Sun. You observe the star over time, and eventually, one of the dimming events begins, the light dropping suddenly and irregularly. The cause remains uncertain, and proposed explanations include clouds of comets, fragments from a disrupted planet, a large ring system around an unseen planet, or even circumstellar dust generated by collisions in the system. The irregular nature of the dimming makes it difficult to model, and the star remains under observation to gather more data and test the various hypotheses. You move away from Boyajian's star and consider the connection to Oumuamua, the first confirmed interstellar object detected passing through our solar system in 2017. Oumuamua was unusual in its shape, possibly elongated or flat, and it showed a small acceleration that could not be explained by gravity alone, suggesting that it was outgassing like a comet or being pushed by radiation pressure. The origin of Oumuamua is unknown, and it may be a fragment from an exoplanet ejected from its home system by a collision or gravitational interaction. You reflect on the possibility that Oumuamua came from a planetary system disrupted by violent events, similar to the scenarios proposed for Boyajian's star, or the temporary dust cloud of Fomalhaut b. The object has now left the solar system and is traveling back into interstellar space. And its brief visit provided only limited data before it moved beyond the reach of telescopes. Future interstellar objects may provide more information, and missions are being planned to intercept such objects if they are detected early enough. You leave these mysteries behind and move to a broader view of the future of exoplanet science. The James Webb Space Telescope is now operational, and it is beginning to reveal detailed atmospheric compositions of exoplanets through high-resolution spectroscopy. Future missions will include telescopes designed specifically for direct imaging of Earth-like planets, and advances in technology will make it possible to detect smaller, cooler, and more distant worlds than current instruments can find. You observe the galaxy stretching out before you, with billions of stars and trillions of planets, many of which remain undiscovered. The strange worlds you have visited represent only a tiny fraction of the diversity that exists, and each new discovery has the potential to reveal phenomena that no one predicted. Planets hotter than stars, planets colder than deep space, planets orbiting dead stars, planets with backward orbits, planets stripped to their cores, planets that should not exist, yet do. The universe creates planets in every imaginable configuration, and some that defy imagination. You drift among the stars, thinking about the 200 facts you have encountered during this journey. Facts about temperatures, orbits, atmospheres, compositions, ages, and mysteries. Facts that reveal the processes that shape planets and the environments in which they exist. The facts are not isolated. They connect to one another, forming a picture of planetary science that is complex, dynamic, and constantly evolving as new discoveries are made and old assumptions are revised. The journey is ending, but the exploration continues. Telescopes on Earth and in space are observing exoplanets every night, measuring their properties, mapping their atmospheres, and searching for signs of habitability. New planets are being discovered every week, and each one adds to the catalogue of worlds that exist beyond our solar system. Some are similar to planets we already know, but others are strange and unexpected, expanding the boundaries of what we thought was possible. You return your attention to the quiet darkness around you, the stars steady and unchanging, the planets invisible from this distance, but present nonetheless, orbiting their stars and following the laws of physics through their long journeys around the galaxy. The strangeness you have witnessed is real. These planets exist. They are out there right now, spinning, orbiting, glowing, freezing, raining glass or iron, locked in place or tumbling through space. The universe is stranger than fiction, and the facts speak for themselves, without need for embellishment or interpretation. The silence of space surrounds you, and the journey through the strangest worlds in the universe comes to a quiet close. The planets remain, distant and unreachable for now, but known, studied, and understood a little more with each observation. You have traveled across light years and billions of years, visiting ancient worlds and newborn planets, scorched rocks and frozen gas giants, orphans and survivors, mysteries and certainties. The universe holds all of them, patiently, waiting for the next discovery, the next strange world that will challenge expectations and expand our understanding of what planets can be.